Deep in the constellation of Cygnus, 670 light-years from Earth, there exists a world so terrifying that it defies every assumption we've ever made about planets. The surface temperature reaches 4600 Kelvin. That's hotter than some stars, hotter than the surface of our own sun. So hot that the very molecules in its atmosphere are literally torn apart atom by atom. This is Kelt 9b, and it represents just the beginning of our journey through the most nightmarish worlds ever discovered. Tonight, we explore planets where iron falls as rain, and where entire worlds are being devoured alive by their own stars. These are the scariest exoplanets too hot to handle. Prepare yourselves. We begin when astronomers first started discovering planets beyond our solar system. They expected to find worlds similar to those in our cosmic neighborhood. Rocky planets like Earth and Mars, gas giants like Jupiter and Saturn. What they found instead was a universe filled with planets so extreme, so hostile, and so alien that they challenge our very understanding of what a planet can be. We call them ultra-hot Jupiters, and they exist in thermal regimes that make Venus look like a winter vacation. These are worlds where the laws of chemistry break down, where metals exist as vapor in the atmosphere, and where the distinction between planet and star becomes terrifyingly blurred. The story begins with temperature. On Earth, we consider a summer day at 100 degrees Fahrenheit to be uncomfortably hot. Water boils at 212 degrees, lead melts at 621 degrees. But the worlds we're about to explore operate in temperature ranges that exceed 7,000 degrees Fahrenheit. These are planets where rocks don't just melt, they vaporize, where the atmosphere itself glows with its own thermal radiation like the coils of an electric stove. Kelt 9b holds the current record as the hottest known exoplanet in the universe. Located 670 light-years away in the constellation Cygnus, this world orbits a massive blue-white star that burns nearly twice as hot as our Sun. The planet completes one orbit in just 36 hours, racing around its stellar host at a distance of only 3.2 million miles. For comparison, Mercury orbits our Sun at 36 million miles, making Kelt 9b more than 10 times closer to its star than Mercury is to the Sun. This proximity creates conditions so extreme they border on the impossible. The dayside temperature reaches 4,027 degrees Celsius. That's 7,820 degrees Fahrenheit. To put this in perspective, this planet is hotter than 40% of all known stars in our galaxy. It's so hot that the distinction between planet and star becomes meaningless in terms of thermal output. But temperature is just the beginning of Kelt 9b's horrors. The extreme heat creates an atmospheric chemistry unlike anything else in the known universe. Hydrogen molecules, the simplest and most stable molecules in nature, cannot survive intact on the day side of this world. The thermal energy is so intense that it literally rips apart the chemical bonds holding hydrogen atoms together, dissociating them into individual atomic components. NASA's Spitzer Space Telescope has provided us with a detailed picture of this molecular destruction. As hydrogen molecules are torn apart on the day side, the individual hydrogen atoms are carried by atmospheric winds to the cooler night side of the planet. There, in the relative coolness of 3,000 degrees Celsius, the atoms can briefly recombine into molecules before the atmospheric circulation carries them back to the day side, where they are immediately destroyed again. This creates a planet-wide cycle of molecular death and rebirth that has been ongoing for millions of years. Imagine an entire world where the fundamental building blocks of chemistry are constantly being assembled and disassembled in an endless cosmic factory of destruction. The hydrogen atoms themselves become witnesses to their own repeated annihilation as they flow around the planet in this thermal dance of death. The atmospheric dynamics of Kelt 9b reveal even more disturbing details. The planet is tidally locked to its star, meaning one side always faces the stellar fire, while the other remains in perpetual darkness. But this doesn't create the stable day-night temperature difference you might expect. Instead, it creates a conveyor belt of destruction, where molecules are systematically manufactured on the night side and fed into the molecular furnace of the day side. Atmospheric models suggest that powerful winds race around the planet at speeds exceeding 5,000 miles per hour, carrying the dissociated atoms from day to night and back again. These aren't gentle breezes carrying water vapor like on Earth. These are supersonic hurricanes of atomic hydrogen, moving at velocities that would make our most violent storms seem like gentle spring rain. The star that Kelt 9b orbits is itself a monster. Kelt 9 is what astronomers classify as a late B-type or early A-type star, meaning it burns much hotter and brighter than our Sun. With a surface temperature of 10,070 Kelvin, or 17,946 degrees Fahrenheit, this stellar furnace pumps out enormous amounts of high-energy ultraviolet radiation that bathes the planet in a constant stream of destructive energy. This radiation doesn't just heat the planet's atmosphere. It actively participates in the molecular destruction process, providing the energy needed to break apart chemical bonds and strip electrons from atoms. The result is an atmosphere that exists in a constant state of chemical chaos, where normal chemistry simply cannot function. But perhaps the most terrifying aspect of Kelt 9b is what's happening to the planet itself. The extreme heating has inflated the planet's atmosphere to nearly twice the radius of Jupiter, despite containing only about 2.8 times Jupiter's mass. This makes Kelt 9b less dense than Jupiter, creating a puffy, bloated world that's literally being cooked from the inside out. The atmospheric expansion has pushed the outer layers of the planet's atmosphere to within 90% of its Roche limit. This is the critical distance where the star's gravitational field becomes stronger than the planet's own gravity. When a planet reaches its Roche limit, its atmosphere begins to be stripped away by the star, creating a stream of escaping material that flows from planet to star like blood from an open wound. Current measurements indicate that Kelt 9b is losing atmospheric mass at a rate of 18 to 68 Earth masses per billion years. To put this in perspective, the planet is losing the equivalent of our entire planet's worth of material every 15 to 55 million years. This mass loss isn't gradual erosion, like wind wearing down a mountain. It's violent atmospheric hemorrhaging that will eventually leave behind only the planet's dense core. The escaping material forms what astronomers call a cometary tail, a stream of vaporized planetary material that extends for millions of miles behind the planet as it orbits its star. Imagine a world so hot that it's literally evaporating into space, leaving a trail of its own substance scattered across the cosmos like cosmic breadcrumbs marking its path of destruction. But Kelt 9b represents just one example of the thermal extremes that planets can endure. Throughout the galaxy, astronomers have discovered dozens of worlds that exist in temperature regimes that challenge our understanding of planetary physics. These ultra-hot Jupiters form a class of planets that simply don't exist in our solar system, worlds where the normal rules of atmospheric chemistry are suspended and replaced by processes so extreme they seem more like stellar physics than planetary science. The discovery of these thermal monsters has forced astronomers to completely rethink their models of planetary formation and evolution. How do planets end up in such close orbits around their stars? How do they survive the intense radiation and tidal forces? And what can these extreme worlds tell us about the limits of planetary existence? The leading theory suggests that ultra-hot Jupiters didn't form where we find them today. Instead, they likely formed much farther from their stars, in the cooler outer regions of their planetary systems where water could condense and help build massive planetary cores. Through a process called planetary migration, gravitational interactions with other planets, or the protoplanetary disk, caused these worlds to spiral inward toward their stars. As they migrated inward, they crossed temperature thresholds that fundamentally changed their nature. First, any water in their atmospheres would have boiled away. Then, more complex molecules began to break apart. Finally, they reached the extreme thermal regimes, where even the simplest molecules cannot survive intact. This migration process explains why ultra-hot Jupiters are found so close to their stars, but it also reveals the tragic nature of their existence. These are worlds that have been forced to abandon the comfortable orbital distances where they formed and dragged into thermal hell by the gravitational dynamics of their planetary systems. They are refugees from the outer system, exiled to regions where survival is barely possible. The study of ultra-hot Jupiters has also revealed the incredible diversity of planetary destruction mechanisms operating throughout the galaxy. While Kelt 9b faces molecular dissociation and atmospheric stripping, other worlds endure different but equally terrifying fates. Some planets are being stretched and distorted by tidal forces until they resemble cosmic eggs more than spheres. Others are experiencing metal rain as iron, and other elements condense out of their superheated atmospheres. Each of these worlds represents a natural experiment in extreme physics, providing astronomers with laboratories for studying matter under conditions that cannot be replicated on Earth, or even in our most advanced particle accelerators. The temperatures and pressures on these planets create exotic states of matter that exist nowhere else in the universe, offering glimpses into physics that operates at the very limits of what matter can endure. But perhaps the most sobering aspect of studying these extreme worlds is what they reveal about planetary mortality. These planets are not just hot, they are dying. The same processes that make them so extreme are also destroying them. Atmospheric stripping, tidal disruption, and thermal expansion are all death sentences being carried out over cosmic timescales. Kelt 9b, despite its current dramatic appearance, has an estimated lifetime of only a few million more years before its atmosphere is completely stripped away. Other ultra-hot Jupiters face even more immediate doom, with some predicted to be consumed by their stars within the next few million years. These are worlds living on borrowed time, their extreme conditions serving as both spectacle and funeral pyre. The discovery of ultra-hot Jupiters has also raised disturbing questions about planetary habitability and the potential for life in extreme environments. While these worlds are clearly hostile to any form of life as we know it, they demonstrate that planets can exist and maintain complex atmospheric chemistry under conditions far more extreme than we previously thought possible. This has implications for our understanding of habitability throughout the galaxy. If planets can survive in such extreme thermal environments, what other supposedly impossible conditions might support worlds with complex atmospheric dynamics? The universe of possible planetary environments may be far stranger and more diverse than we ever imagined. As we continue our journey through the scariest exoplanets too hot to handle, Kelt 9b serves as our introduction to a universe where normal physics breaks down and planets exist in states that blur the line between world and star. But this molecular furnace, terrifying as it is, represents just the beginning of the thermal horrors that await us in the cosmic deep. The next world on our journey takes us even deeper into the realm of planetary destruction, where we'll encounter a planet so close to its star that it's being physically reshaped by gravitational forces while simultaneously being devoured alive. This is a world where the very geometry of space-time conspires to create the ultimate expression of planetary doom. Beyond the molecular furnace of Kelt 9b lies a world caught in the ultimate cosmic death spiral. WASP 12b, orbits its star so closely that the very fabric of space-time has become a weapon of mass destruction, warping the planet into shapes that defy our understanding of celestial mechanics. This is not just a hot planet. This is a world being murdered by the universe itself. Located 871 light-years from Earth. In the constellation Auriga, WASP-12b completes one orbit around its star in just 26 hours. But calling this an orbit understates the violence of what's actually happening. The planet races around its stellar host at a distance of only 2.1 million miles, so close that the star's gravity has begun to physically reshape the world from a sphere into something resembling a cosmic egg. The gravitational forces at work here operate beyond anything we experience in our solar system. Tidal forces, the same gentle influences that create Earth's ocean tides, become instruments of planetary torture when amplified to these extreme levels. The side of WASP-12b facing its star experiences gravitational pull nearly 100 times stronger than the force on the planet's far side. This differential creates what astronomers call tidal bulging, where the planet is literally stretched along the axis pointing toward its star. But this isn't the gradual reshaping of geological timescales. This is violent, ongoing deformation that transforms a once spherical world into an elongated mass of superheated gas and plasma. The planet's equatorial diameter has been stretched to nearly twice its polar diameter, creating an egg-shaped monstrosity that rotates through space like a cosmic football. The surface temperature of this deformed world reaches 4,000 degrees Fahrenheit, hot enough to melt copper and vaporize most known materials. But temperature is just one component of WASP-12b's torment. The tidal forces that reshape its geometry also create internal friction that heats the planet from within, adding thermal energy to an already blazing inferno. As the planet stretches and contracts with each orbit, the movement of material within its interior generates enormous amounts of heat through gravitational compression and release. This process, known as tidal heating, turns the entire planet into a cosmic stress ball being squeezed and released by invisible hands made of pure gravitational force. The star WASP-12, a G-type star similar to our Sun but slightly larger and hotter, doesn't just heat and deform its planetary companion. It actively consumes it. The extreme tidal forces have stretched WASP-12b's atmosphere beyond its Roche limit, the critical boundary where the star's gravity overcomes the planet's ability to hold on to its own material. Material from the planet's outer atmosphere now streams toward the star in a continuous flow of vaporized rock and metal. This isn't atmospheric escape like we see on Kelt 9b. This is atmospheric hemorrhaging on a scale that defies comprehension. The planet loses approximately 189 quadrillion tons of material every year, equivalent to the mass of 6 billion tons per second flowing from planet to star. To visualize this cosmic cannibalism, imagine a waterfall where instead of water, molten rock and vaporized metals cascade through space at temperatures exceeding 4,000 degrees. This stellar feast has been ongoing for millions of years, with the star slowly but systematically devouring its planetary companion, one atom at a time. The Hubble Space Telescope has captured direct images of this planetary consumption in action. Observations reveal a stream of material, primarily hydrogen and helium, stripped from the planet's atmosphere, flowing from WASP-12b toward its star. This material forms an accretion stream that glows with its own thermal radiation as it spirals into the stellar furnace. But the horror of WASP-12b's situation extends beyond simple mass loss. The planet exists in what astronomers call a feedback loop of destruction. As it loses mass, its gravitational field weakens, making it even more vulnerable to tidal stripping. As tidal forces remove more material, the planet becomes less dense and more easily deformed, accelerating the destruction process. Current calculations indicate that WASP-12b has between 2.9 and 10 million years remaining before it is completely consumed by its star. In cosmic terms, this represents the final moments of a world's existence. The planet is experiencing its own apocalypse in slow motion, stretched and devoured across geological timescales that span millions of human lifetimes. The destruction of WASP-12b reveals the ultimate fate awaiting any planet that ventures too close to its stellar host. The same gravitational forces that hold planetary systems together become instruments of annihilation when the delicate balance between orbital mechanics and stellar gravity is disrupted. Scientists have detected subtle changes in WASP-12b's orbital period that confirm the planet's death spiral. Each orbit brings the world approximately 29 milliseconds closer to its star, a seemingly tiny change that represents the inexorable march towards stellar consumption. This orbital decay will accelerate as the planet loses more mass, creating a runaway process that ends only when the last fragments of the world disappear into the stellar furnace. The chemical composition of the material being stripped from WASP-12b tells a story of planetary destruction written in atomic signatures. Spectroscopic analysis reveals the presence of carbon, oxygen, and heavier elements being torn from the planet's atmosphere and absorbed by the star. These are the building blocks of worlds being recycled through stellar nucleosynthesis, the ashes of a dying planet becoming fuel for continued stellar burning. Perhaps most disturbing is the realization that WASP-12b was once a normal gas giant, possibly similar to Jupiter or Saturn. The planet likely formed in the outer regions of its stellar system, where temperatures were cool enough for water ice to condense and help build massive planetary cores. Through some catastrophic event, possibly gravitational interactions with other planets or stellar companions, WASP-12b was forced to migrate inward to its current hellish orbit. This migration transformed a once stable world into the cosmic horror we observe today. The planet's journey from the comfortable outer system to its current position represents one of the most tragic stories in planetary science, a tale of exile and slow destruction that spans millions of years. The study of WASP-12b has also revealed the incredible precision with which gravitational forces operate across cosmic distances. The tidal effects that deform and destroy this planet are calculated with mathematical exactness, following the same physical laws that govern ocean tides on Earth. But scaled up to planetary dimensions, these gentle forces become cosmic torture devices capable of reshaping entire worlds. Advanced computer simulations of WASP-12b's destruction process reveal the intricate dance between gravitational physics and thermodynamics that drives the planet's demise. As tidal forces stretch the planet's atmosphere, they create temperature gradients that drive powerful atmospheric circulation patterns. These winds, moving at speeds of thousands of miles per hour, redistribute heat and material around the planet while simultaneously feeding the stellar accretion stream. The atmospheric dynamics of WASP-12b create weather patterns unlike anything in our solar system. Instead of rain clouds, this world experiences precipitation of vaporized rock and metal. Instead of seasonal changes, it undergoes constant atmospheric stripping that varies only in intensity as the planet's elliptical orbit brings it closer to or farther from its star. Temperature measurements across the planet's surface reveal the extreme thermal gradients created by tidal heating and stellar irradiation. The point on the planet's surface closest to the star, known as the substellar point, reaches temperatures exceeding 5,000 degrees Fahrenheit. The planet's poles, while still impossibly hot by Earth standards, remain several hundred degrees cooler, creating thermal differences that drive atmospheric circulation patterns of unprecedented violence. But WASP-12b's story also provides crucial insights into planetary formation and migration processes throughout the galaxy. The planet's current predicament results from gravitational dynamics that operate in countless stellar systems, suggesting that worlds like WASP-12b may be common throughout the universe. Every close-orbiting planet we discover represents a potential future victim of the same tidal destruction processes. The fate of WASP-12b serves as a cosmic cautionary tale about the fragility of planetary systems and the ultimate power of stellar gravity. No matter how massive or well-established a planet might be, venturing too close to a star triggers destruction mechanisms that operate with the inevitability of physical law. These are not random cosmic accidents, but predictable consequences of orbital mechanics carried to their logical extreme. As we witness WASP-12b's ongoing destruction, we observe one of the universe's most fundamental processes: the conversion of planetary matter back into stellar fuel. The atoms that once comprised solid ground and gaseous atmosphere are being systematically disassembled and fed into nuclear fusion reactions that will power the star for millions of years to come. This cosmic recycling process reveals the ultimate impermanence of planetary systems. Worlds that took millions of years to form can be unmade in equally vast timescales. Their constituent atoms return to the stellar furnaces where they were originally forged. WASP-12b's destruction represents not just the death of a single planet, but a glimpse into the eventual fate that awaits all matter in the universe. The gravitational death spiral consuming WASP-12b will continue until the final fragments of the planet merge with its star in approximately 3 million years. When that moment arrives, the star will briefly flare brighter as it digests the last remnants of its planetary companion, creating a cosmic funeral pyre visible across interstellar distances. But even as WASP-12b approaches its final doom, it continues to teach us about the extreme conditions that planets can endure. The world's survival, even in its current tortured state, demonstrates the remarkable resilience of planetary atmospheres under conditions that should theoretically destroy them instantly. This resilience hints at the possibility that planets might survive in other extreme environments we haven't yet considered, expanding our understanding of where worlds might exist and what forms they might take. If a planet can maintain atmospheric structure while being actively consumed by its star, what other impossible conditions might harbor complex planetary systems? The lessons learned from WASP-12b's destruction extend far beyond academic curiosity. As our technology advances and we begin to discover Earth-sized planets around distant stars, understanding the processes that destroy worlds becomes crucial for identifying those that might remain stable long enough to develop and sustain life. WASP-12b stands as a monument to planetary mortality, a world whose destruction illuminates the cosmic forces that shape the galaxy. Its egg-shaped silhouette, stretched between existence and annihilation, serves as a reminder that even planets are temporary features in the universe's grand design. As WASP-12b spirals toward its inevitable doom, scattered throughout the galaxy are worlds experiencing even more exotic forms of destruction. These are planets where the very elements that should remain solid under normal conditions have been transformed into weapons of atmospheric violence. Welcome to the realm of metal rain and iron winds, where the periodic table itself becomes a forecast of terror. 634 light-years from Earth, in the constellation Pisces, orbits a world that redefines our understanding of weather. WASP-76b experiences day and night in ways that would make the most extreme earthly storms seem like gentle spring showers. On the permanently illuminated side of this tidally locked planet, temperatures soar to 4,400 degrees Fahrenheit, hot enough to vaporize iron and transform solid metals into gaseous components of the atmosphere. But the true horror of WASP-76b reveals itself not in its scorching dayside temperatures, but in what happens when that superheated metallic vapor encounters the planet's eternal night. As powerful atmospheric winds carry iron-laden air from the blazing day side around to the cooler night side, the vaporized metal begins to condense. What falls from the alien skies is not water or snow, but droplets of molten iron raining down like a cosmic foundry gone mad. Imagine standing beneath clouds that glow with their own thermal radiation, watching as liquid metal droplets the size of raindrops cascade from the heavens at temperatures exceeding 2,000 degrees. This is not the gentle precipitation that nourishes life on Earth. This is industrial rain forged in atmospheric furnaces and delivered by winds that howl across the planet at supersonic speeds. The European Southern Observatory's espresso spectrograph has provided us with detailed observations of this metallic precipitation in action. The instrument can detect the spectroscopic signatures of iron atoms as they move through WASP-76b's atmosphere, revealing wind patterns and temperature gradients that drive this extraordinary weather system. The iron rain of WASP-76b operates on a planetary scale that dwarfs any earthly weather phenomenon. The total mass of iron cycling through this world's atmosphere exceeds the combined mass of all iron ore deposits on Earth. Every second, millions of tons of molten metal flow through atmospheric circulation patterns that span the entire planet. But iron represents just one component of WASP-76b's metallic atmosphere. Spectroscopic analysis has revealed the presence of 11 different chemical elements vaporized in the planet's upper atmosphere, including magnesium, chromium, manganese, and titanium. These are elements that form the bedrock of terrestrial worlds, transformed into atmospheric gases by temperatures that exceed those found in steel foundries. The atmospheric chemistry of WASP-76b creates conditions so extreme they challenge our understanding of how matter behaves under intense heat and pressure. Titanium oxide, normally found in mineral deposits and industrial ceramics, exists as a gas in this world's atmosphere. Vanadium oxide, detected for the first time on any exoplanet, floats through the alien air like a metallic fog. These exotic atmospheric components interact with stellar radiation in ways that create optical effects impossible anywhere else in the universe. The metallic gases absorb and scatter light across specific wavelengths, creating atmospheric colors and phenomena that would appear alien and beautiful if they weren't so thoroughly lethal. The day-night temperature differential on WASP-76b drives atmospheric circulation patterns of unprecedented violence. Winds racing around the planet at speeds exceeding 11,000 miles per hour carry not just heat and moisture, but entire periodic tables worth of vaporized elements. These supersonic metal-laden hurricanes make Earth's most powerful storms seem like gentle breezes. The planet's proximity to its host star, orbiting at a distance 12 times closer than Mercury orbits our Sun, creates the extreme heating necessary to maintain this metallic weather system. The star, WASP-76, slightly larger and hotter than our Sun, bathes the planet in radiation intense enough to keep heavy metals in gaseous form across vast regions of the atmosphere. But the metal rain phenomenon extends beyond simple precipitation. The cooling and condensation of metallic vapors creates what astronomers call chemical weather fronts, boundaries between regions of different atmospheric composition that move across the planet like cosmic storm systems. These fronts separate zones where different metals condense, creating a patchwork of metallic precipitation that changes with atmospheric dynamics. Advanced atmospheric models suggest that WASP-76b experiences seasonal variations in its metal rain patterns, despite being tidally locked to its star. Changes in the planet's orbital distance and stellar output create subtle variations in temperature that alter which metals can remain gaseous and which condense into precipitation. The discovery of metal rain planets has revolutionized our understanding of atmospheric chemistry under extreme conditions. These worlds serve as natural laboratories for studying metallurgy and phase transitions under conditions impossible to replicate on Earth. The temperatures and pressures that drive metallic precipitation on these planets provide insights into industrial processes and materials, science that could advance human technology. But WASP-76b represents just one example of the exotic precipitation phenomena occurring throughout the galaxy. Other ultra-hot planets experience even more unusual forms of atmospheric chemistry, including worlds where diamonds form in the upper atmosphere and rain down like precious gemstone hail. The atmospheric dynamics that create metal rain also produce other exotic weather phenomena. Lightning on WASP-76b, if it exists, would arc between clouds of vaporized metal at temperatures hot enough to melt tungsten. Thunder would propagate through an atmosphere dense with metallic vapors, creating acoustic phenomena unlike anything in our solar system. The magnetic field interactions on metal rain planets create additional complications for atmospheric dynamics. The movement of electrically conductive metallic vapors through magnetic fields generates electrical currents that can influence atmospheric circulation patterns. These magnetohydrodynamic effects add another layer of complexity to already chaotic weather systems. Temperature measurements across WASP-76b's surface reveal the precision with which atmospheric chemistry operates under extreme conditions. The boundary between the day and night sides, known as the terminator line, marks the transition zone where metal vapors begin to condense. This boundary acts like a cosmic weather front thousands of miles wide, separating the vaporization zone from the precipitation zone. The study of metal rain planets has also revealed the incredible efficiency of atmospheric heat transport under extreme conditions. Despite temperature differences of over 2,000 degrees between day and night sides, the powerful atmospheric circulation redistributes thermal energy with remarkable effectiveness. The metallic atmosphere acts like a planetary-scale heat engine, converting temperature differentials into kinetic energy that drives the wind systems. Recent observations have detected temporal variations in the metal rain patterns on WASP-76b, suggesting that these atmospheric systems are not static but undergo dynamic changes over time. These variations might result from stellar activity, orbital perturbations, or internal atmospheric instabilities that create evolving weather patterns. The longevity of metal rain planets raises intriguing questions about atmospheric stability under extreme conditions. Despite the violent temperature swings and chemical processes occurring in their atmospheres, these worlds maintain coherent atmospheric structures across geological timescales. This stability suggests that even the most extreme atmospheric chemistry can reach equilibrium states that persist for millions of years. The implications of metal rain extend beyond individual planets to entire stellar systems. The atmospheric stripping and chemical processing occurring on these worlds redistributes heavy elements throughout their stellar neighborhoods. Material lost from metal rain planets can be incorporated into stellar winds, interplanetary dust, and even the formation of new planets in the same system. But perhaps the most remarkable aspect of metal rain planets is their role as cosmic alchemists. The extreme temperatures and pressures in their atmospheres create conditions where nuclear processes beyond simple chemical reactions might occur. High-energy particle interactions in these metallic atmospheres could theoretically produce isotopes and chemical compounds that exist nowhere else in nature. The discovery of increasingly exotic metal rain planets continues to expand our catalog of atmospheric extremes. Recent observations have identified worlds where aluminum, calcium, and even rare earth elements participate in precipitation cycles. Each new discovery reveals atmospheric chemistry, operating at temperature and pressure regimes that push the boundaries of what planetary science considered possible. As we venture deeper into the realm of thermal extremes, metal rain planets like WASP-76b serve as waypoints marking our journey toward even more extraordinary worlds. These metallic precipitation systems, violent as they are, represent stable atmospheric processes compared to the cosmic horrors that await us in the darkest regions of planetary science. Beyond the iron storms and metallic hurricanes lies a world so dark it absorbs light itself, yet burns with temperatures that would vaporize lead. This is a planet that challenges our understanding of how matter and energy interact under the most extreme conditions imaginable, where darkness and fire merge into a single expression of cosmic terror. The darkest world ever discovered lurks in the constellation Draco, 750 light-years from Earth. Tris 2b reflects less than 1% of the light that strikes it, making it darker than charcoal, darker than black acrylic paint, darker than any known material in our solar system. Yet this world of absolute darkness burns with internal fire, glowing like a cosmic ember with temperatures exceeding 1,800 degrees Fahrenheit. This paradox of darkness and heat creates one of the most unsettling combinations in the known universe. Tris 2b appears as a sphere of pure black that radiates its own faint red glow, like looking at a coal fresh from the furnace or the heating elements of an electric stove. The planet absorbs virtually all incoming starlight while simultaneously emitting thermal radiation from its superheated interior. The extreme darkness of Tris 2b results from an atmospheric chemistry unlike anything found elsewhere in the galaxy. The planet's upper atmosphere contains vaporized sodium, potassium, and titanium oxide, compounds that absorb light across virtually the entire electromagnetic spectrum. These metallic vapors act like atmospheric black paint, trapping photons and converting their energy into heat rather than reflecting them back to space. But the absorption of light represents only part of Tris 2b's thermal story. The planet orbits its sun-like host star at a distance of just 3.1 million miles, completing one orbit every 2.5 days. This proximity subjects the world to stellar radiation intense enough to maintain surface temperatures that would melt copper and vaporize most organic compounds. The combination of extreme light absorption and close stellar proximity creates a runaway heating process that transforms Tris 2b into a cosmic heat sink. Every photon that strikes the planet's surface is absorbed and converted to thermal energy, with virtually none reflected back to space. This perfect light absorption makes the planet an ideal black-body radiator, emitting thermal radiation with maximum efficiency. The internal structure of Tris 2b compounds its thermal extremes. As a gas giant with approximately the same mass as Jupiter but orbiting much closer to its star, the planet experiences intense tidal heating that generates additional thermal energy from within. Gravitational forces from the nearby star constantly flex and compress the planet's interior, converting mechanical energy into heat through friction and compression. This tidal heating, combined with the absorbed stellar radiation, creates temperature gradients within the planet that drive convection currents of unprecedented scale. Massive plumes of superheated gas rise from the planet's interior while cooler material sinks, creating circulation patterns that span the entire planetary diameter. The atmospheric composition that creates Tris 2b's extreme darkness also produces exotic chemical processes operating at the boundary between chemistry and physics. At temperatures exceeding 800 degrees Fahrenheit, titanium oxide exists in gaseous form and participates in atmospheric reactions that would be impossible under cooler conditions. These high-temperature chemical processes create what astronomers call opacity sources, atmospheric components that selectively absorb light at specific wavelengths. The titanium oxide and vaporized metals in Tris 2b's atmosphere create opacity, across virtually the entire visible spectrum, explaining why the planet appears so uniformly dark when observed from Earth. But the darkness of TRES-2b extends beyond simple light absorption. The planet's atmospheric chemistry creates what scientists call negative albedo effects, where certain atmospheric components not only absorb incoming light, but also suppress the planet's ability to reflect light at other wavelengths. This creates a feedback loop that makes the planet darker than it would be through simple absorption alone. Recent spectroscopic observations have revealed additional exotic compounds in TRES-2b's atmosphere, including gaseous forms of elements that typically exist only in solid form under normal conditions. The extreme temperatures have vaporized calcium, magnesium, and even iron, creating an atmospheric soup of metallic vapors that contributes to the planet's light-absorbing properties. The thermal emission from TRES-2b provides astronomers with a unique window into the physics of heat radiation under extreme conditions. The planet's surface temperature, while not hot enough to emit visible light efficiently, produces infrared radiation that can be detected by sensitive space-based telescopes. This thermal glow reveals temperature variations across the planet's surface and provides clues about atmospheric circulation patterns. Temperature mapping of TRES-2b has revealed that the planet's hotspot, the region of maximum temperature, is offset from the point directly facing the star. This offset suggests powerful atmospheric winds that transport heat around the planet faster than the world rotates. These wind systems, driven by temperature differentials and pressure gradients, create weather patterns that operate on a planetary scale. The study of TRES-2b has also provided insights into the limits of planetary heating and cooling processes. Despite absorbing virtually all incident stellar radiation, the planet maintains thermal equilibrium by radiating energy away as infrared light. This balance between energy absorption and emission reveals the fundamental physics governing planetary temperature regulation. Advanced atmospheric models suggest that TRES-2b's darkness results from a precise balance of atmospheric chemistry that could be disrupted by relatively small changes in temperature or stellar radiation. If the planet's orbit were to change slightly, bringing it closer to or farther from its star, the atmospheric composition could shift dramatically, potentially altering the world's light-absorbing properties. The longevity of TRES-2b's extreme darkness raises questions about atmospheric stability under such exotic conditions. The chemical processes that maintain the planet's light-absorbing atmosphere must operate continuously to replace compounds that are destroyed by stellar radiation or lost to space through atmospheric escape. Comparative studies of TRES-2b and other ultra-hot planets have revealed that extreme darkness is relatively rare among exoplanets. Most hot Jupiters reflect at least some incident light, making TRES-2b's near-perfect absorption an unusual and possibly temporary phenomenon. The planet might represent a specific phase in the evolution of ultra-hot atmospheric chemistry. The discovery of TRES-2b has inspired laboratory experiments aimed at recreating the extreme atmospheric conditions that produce such perfect light absorption. These experiments use high-temperature ovens and controlled atmospheres to study how metallic vapors behave under conditions similar to those found on the planet. Results from these laboratory studies have confirmed that gaseous titanium oxide and other metallic compounds can indeed create near-perfect light absorption across broad wavelengths when present in sufficient concentrations. The experiments also reveal that maintaining these conditions requires precise temperature and pressure control, suggesting that TRES-2b's atmospheric chemistry operates within narrow stability ranges. The implications of perfect light absorption extend beyond planetary science to technologies for solar energy collection and thermal management. Understanding how TRES-2b achieves such efficient light absorption could inspire new materials and surfaces designed for maximum energy capture and conversion. But perhaps the most profound aspect of TRES-2b is its demonstration that planets can exist in states that seem to contradict basic expectations about planetary behavior. A world that appears completely dark, yet burns with internal fire, challenges our preconceptions about how planets should look and behave under extreme conditions. The paradox of TRES-2b serves as a reminder that the universe contains phenomena that operate according to physical laws while producing results that seem impossible or contradictory. This dark world that glows with its own heat represents just one example of the cosmic extremes that await discovery as our understanding of exoplanetary science continues to expand. As we prepare to encounter worlds that face even more immediate and violent destruction, TRES-2b stands as an example of how planets can maintain stable yet extreme conditions across geological timescales. Its perfect darkness and internal fire create a unique thermal environment that has persisted for millions of years, demonstrating the remarkable range of stable states that planetary atmospheres can achieve. The journey from molecular furnaces through gravitational death spirals and metal rainstorms to worlds of perfect darkness has revealed the incredible diversity of extreme planetary environments. But these thermal nightmares represent only the beginning of our exploration into the scariest exoplanets too hot to handle. Beyond the realm of stable extremes lies a category of worlds facing immediate and catastrophic destruction, planets whose very existence challenges the limits of what matter can endure before crossing the threshold into complete annihilation. In the outer reaches of the Neptunian desert, a region of space where planets of certain sizes simply cannot survive, astronomers have discovered worlds that exist in defiance of cosmic law. These are planets that should not exist, yet continue to burn in thermal regimes that push the very boundaries of what matter can endure before crossing into complete destruction. The Neptunian desert represents one of the most mysterious phenomena in exoplanet science. This is a region close to stars where planets with masses between 10 and 250 Earth masses and orbital periods shorter than 4 days are spectacularly rare. It's as if the universe has declared certain combinations of planetary size and stellar proximity to be forbidden, creating cosmic no-man's lands where worlds of particular characteristics simply cannot survive. Yet within this desert of impossibility, we find exceptional survivors. TOE 849b orbits its star every 18 hours at a distance so close that its equilibrium temperature reaches 2,781 degrees Fahrenheit. This world is 40 times more massive than Earth, but only 3 times larger in diameter, creating a density so extreme that it rivals the rocky cores of terrestrial planets rather than the fluffy atmospheres of gas giants. What makes TOI 849b truly terrifying is not what it is, but what it represents. This planet is believed to be the exposed core of a former gas giant, a world that once possessed a massive atmospheric envelope that has been completely stripped away by stellar winds and radiation. We are looking at the naked heart of a dead planet, the dense, rocky center that once lay buried beneath thousands of miles of gaseous atmosphere. The process that created TOI 849b represents one of the most violent forms of planetary death imaginable. Atmospheric stripping on this scale doesn't happen gradually. It requires catastrophic events that can remove entire atmospheric envelopes in geological instants. The planet may have suffered a collision with another world, experienced extreme stellar flares, or undergone runaway atmospheric escape that left only its dense core behind. Standing on the surface of TOI 849b, if such a thing were possible, would reveal a landscape unlike anything in our solar system. The exposed planetary core consists of compressed rock and metal that once formed the foundation beneath miles of hydrogen and helium atmosphere. The surface gravity would be crushing, over 10 times stronger than Earth's, while temperatures would exceed those found in commercial furnaces. The discovery of exposed planetary cores like TOI 849b has revealed that atmospheric destruction can be far more complete than previously imagined. Most atmospheric loss processes remove material gradually over millions of years. But the complete stripping that created these naked cores suggests destruction mechanisms so powerful they can dismantle entire atmospheric systems in cosmic moments. Computer simulations of core exposure reveal the incredible violence required to achieve such complete atmospheric removal. The energy involved in stripping away thousands of miles of gaseous envelope exceeds the total energy output of most stars over periods of years. This energy must be delivered precisely and rapidly enough to overcome the planet's gravitational binding energy and blast the entire atmosphere into space. The survival of these exposed cores provides crucial insights into planetary internal structure. TOI 849b demonstrates that gas giant planets possess solid cores capable of maintaining structural integrity even after losing their atmospheric envelopes. These cores represent the original solid foundations around which the gas giants originally formed, now revealed like archaeological artifacts of planetary construction. But atmospheric stripping represents just one pathway to planetary destruction, operating in the thermal extremes of close stellar orbits. Other worlds face even more immediate and spectacular forms of annihilation through processes that operate on timescales measured in millions rather than billions of years. HD Tauhanta 9-58b, located 159 light-years from Earth in the constellation Pegasus, is experiencing atmospheric escape so severe that it has earned the nickname Osiris, after the Egyptian god associated with death and rebirth. This world is literally evaporating into space, creating a comet-like tail of escaping atmosphere that extends for millions of miles behind the planet as it orbits its star. The atmospheric escape from HD 29458b occurs through a process called hydrodynamic escape, where the entire upper atmosphere expands and flows away from the planet like water from a broken dam. High-energy ultraviolet radiation from the planet's host star heats the upper atmosphere to temperatures exceeding 18,000 degrees Fahrenheit, causing hydrogen and helium to achieve escape velocity and stream away into space. This escaping material creates one of the most spectacular phenomena in planetary science. The planet's atmospheric tail, composed of hydrogen atoms glowing under stellar radiation, extends for over 120,000 miles behind the world as it orbits its star. This tail is visible to space-based telescopes as a ghostly stream of light marking the path of a dying world. The rate of atmospheric loss from HD 29458b approaches 10,000 tons per second, a hemorrhaging of planetary material that will eventually leave behind only the planet's rocky core. Current estimates suggest the planet loses approximately 100 million tons of atmosphere per day, a rate of destruction that would strip away Earth's entire atmosphere in less than 50,000 years. But the atmospheric escape from HD 29458b reveals more than simple mass loss. Spectroscopic analysis of the escaping material has detected oxygen, carbon, silicon, and other heavy elements being dragged away from the planet by the escaping hydrogen. This means the planet is losing not just its light atmospheric gases, but also the heavier elements that form the building blocks of solid worlds. The discovery of heavy element escape has revolutionized our understanding of how atmospheric stripping affects planetary composition. When light gases like hydrogen and helium escape from a planet, they can drag heavier atoms along with them through a process called hydrodynamic drag. This means that atmospheric escape can fundamentally alter a planet's chemical composition over time. Advanced atmospheric models suggest that HD 29458b has already lost a significant fraction of its original mass to space. The planet may have begun its existence as a much more massive world before stellar radiation began the slow process of atmospheric destruction. We are witnessing a planet in the advanced stages of evaporation, a world whose ultimate fate is to become another exposed core like TOI 849b. The study of evaporating planets has revealed the incredible precision with which stellar radiation can dismantle planetary atmospheres. The wavelengths of ultraviolet light that drive atmospheric escape correspond exactly to the energy levels required to heat atmospheric gases to escape velocity. It's as if stars possess surgical tools designed specifically for planetary destruction. Temperature measurements across HD 29458b's escaping atmosphere reveal the complex physics governing hydrodynamic escape. The base of the escaping atmosphere, where it connects to the planet's main atmospheric envelope, maintains temperatures around 1,800 degrees Fahrenheit, but as the gas expands and accelerates away from the planet, temperatures rise to over 18,000 degrees Fahrenheit, hot enough to ionize hydrogen atoms and create plasma. This temperature gradient creates what astronomers call an atmospheric blow-off zone, a region where the normal rules of atmospheric physics break down and gas dynamics become dominated by escape processes. In this zone, the atmosphere transitions from bound planetary material to free-streaming gas flowing away into interplanetary space. The magnetic field interactions between escaping planetary atmospheres and stellar winds create additional complexity in the destruction process. As charged particles in the escaping atmosphere encounter the star's magnetic field, they can be accelerated to even higher velocities or deflected into complex trajectories that affect the shape and extent of the atmospheric tail. Recent observations have detected variability in the atmospheric escape rate from HD 29458b, suggesting that the destruction process is not constant, but varies with stellar activity and planetary orbital position. During periods of high stellar activity, the escape rate can increase dramatically as enhanced ultraviolet radiation drives more vigorous atmospheric heating. The temporal variations in atmospheric escape reveal that planetary destruction through evaporation is not a smooth, gradual process, but rather a series of violent episodes punctuated by periods of relative stability. This episodic destruction means that planets like HD 20945-8b experience alternating periods of catastrophic mass loss and temporary reprieve. The discovery of multiple evaporating planets throughout the galaxy has revealed that atmospheric escape represents one of the most common forms of planetary death in the universe. Any planet orbiting close enough to its star to experience significant ultraviolet radiation faces the eventual loss of its atmospheric envelope through hydrodynamic escape processes. But evaporating planets also serve as natural laboratories for studying atmospheric physics under extreme conditions. The escaping atmospheres provide direct samples of planetary material that can be analyzed spectroscopically to determine atmospheric composition, temperature structure, and escape dynamics with unprecedented precision. The study of HD 29458b and similar evaporating worlds has also revealed the role of planetary mass in determining survival against atmospheric stripping. More massive planets possess stronger gravitational fields that can retain their atmospheres against stellar radiation, while less massive worlds are more vulnerable to complete atmospheric loss. This mass dependence explains the existence of the Neptunian desert and similar gaps in the exoplanet population. Planets with intermediate masses face a cosmic catch-22. They are too small to retain their atmospheres against stellar radiation, but too large to survive as rocky worlds without atmospheric protection. These intermediate mass planets are systematically destroyed by atmospheric escape, creating the observed gaps in planetary populations. The fate of evaporating planets depends critically on their internal structure and composition. Planets with substantial rocky cores may survive atmospheric stripping to become super-Earths, or exposed cores like TOI 849b. But planets with small cores relative to their atmospheric mass may be completely destroyed, leaving behind no trace of their former existence. The complete destruction of planets through atmospheric escape represents the ultimate expression of stellar power over planetary systems. Stars that appear gentle and life-giving from Earth's comfortable distance become instruments of planetary annihilation when planets venture too close to their deadly embrace. As we witness the slow-motion destruction of worlds like HD 29458b, we observe one of the universe's most fundamental processes: the conversion of planetary matter back into the interstellar medium from which it originally formed. The atoms that once comprised solid ground and breathable atmosphere are being systematically returned to space, where they may eventually be incorporated into new generations of stars and planets. This cosmic recycling process reveals the ultimate impermanence of planetary systems and the dynamic nature of matter in the universe. Even the most stable-seeming worlds are temporary arrangements of atoms that will eventually be redistributed through stellar and galactic processes operating over cosmic timescales. The atmospheric tails of evaporating planets serve as visible reminders of this cosmic impermanence, ghostly streams of light marking the paths of worlds in their final death throes. These tails stretch across millions of miles of space, creating monuments to planetary destruction that can be observed from across the galaxy. But perhaps the most sobering aspect of studying evaporating planets is the realization that atmospheric escape operates according to predictable physical laws. Given a planet's mass, orbital distance, and stellar radiation environment, astronomers can calculate with mathematical precision how long the world will survive before its atmosphere is completely stripped away. This predictability transforms planetary destruction from a random cosmic accident into an inevitable consequence of orbital mechanics and stellar physics. Every close-orbiting planet faces a calculable death sentence, with execution carried out by the inexorable processes of atmospheric escape over timescales that span millions of years. The study of planets in their final death throes has also revealed the incredible diversity of destruction mechanisms operating throughout the galaxy. While some worlds die through atmospheric stripping, others face tidal disruption, stellar consumption, or collision with other planets. Each mechanism operates according to different physical principles, but achieves the same ultimate result: the complete destruction of worlds that once orbited peacefully around their stars. As our journey through the scariest exoplanets too hot to handle approaches its climax, the evaporating worlds like HD 29458b serve as harbingers of even more extreme destruction processes. These planets, violent as their deaths may be, still maintain recognizable atmospheric structure during their destruction. But beyond the realm of evaporating atmospheres lie worlds facing forms of annihilation so complete and immediate that they challenge our very definition of what constitutes a planet. In the final circle of planetary hell, we encounter worlds whose destruction operates not over millions of years, but over thousands. These are planets caught in gravitational death spirals so tight that their orbital decay can be measured from Earth. Worlds whose remaining lifetimes can be calculated with the precision of a countdown timer, marking their approach to stellar consumption. In the constellation Centaurus, 390 light-years from Earth, a world named WASP 18b races toward its final appointment with destruction. This planet completes one orbit around its star in just 22.6 hours, but each orbit brings it measurably closer to its stellar grave. The orbital decay is so rapid that astronomers can detect the change from Earth. watching as this world spirals toward annihilation with the precision of a cosmic stopwatch counting down to zero. WASP 18b represents the ultimate expression of planetary mortality, a world so close to its star that tidal forces have locked it into an inescapable death spiral. The planet orbits at a distance of just 1.9 million miles from its stellar host, so close that the star's gravity has begun to tear the world apart from the inside out. Every orbit strips away a fraction of the planet's orbital energy, causing it to spiral inward toward inevitable destruction. The physics governing WASP 18b's death spiral operate with mathematical precision that would be beautiful if it weren't so terrifying. As the planet orbits its star, tidal forces create bulges in both the planetary and stellar surfaces. These bulges don't align perfectly with the line connecting planet and star, creating a slight gravitational lag that acts like cosmic friction, steadily robbing the planet of orbital energy. This energy loss manifests as orbital decay measured in milliseconds per year, a seemingly tiny change that accumulates into planetary catastrophe over cosmic timescales. Current measurements indicate that WASP 18b's orbital period is decreasing by approximately 91 milliseconds per century, a rate of decay that will bring the planet into contact with its star's outer atmosphere in just 650,000 years. 650,000 years might seem like an enormous span of time from a human perspective, but in cosmic terms, this represents the final moments of a world's existence. WASP 18b is experiencing planetary old age and fast forward, its remaining lifetime shorter than the time it took for complex life to evolve on Earth. The star that WASP 18b orbits is itself a monster, containing 1.25 times the mass of our Sun, but burning much hotter and brighter. This stellar furnace subjects the planet to radiation so intense that surface temperatures exceed 4,200 degrees Fahrenheit, hot enough to vaporize most known materials and maintain atmospheric chemistry that operates more like stellar physics than planetary science. But temperature represents just one component of WASP 18b's torment. The planet's proximity to its star creates tidal forces so extreme they literally reshape the world's interior structure. The gravitational differential between the planet's near and far sides generates internal friction that heats the planetary interior to temperatures exceeding those found in Earth's core. This tidal heating transforms the entire planet into a cosmic stress ball being squeezed and released with each orbit. The mechanical energy generated by this constant deformation adds thermal energy to an already blazing world, creating a feedback loop where gravitational torture generates additional heat that further destabilizes the planet's structure. Advanced computer simulations of WASP 18b's final fate reveal the sequence of events that will unfold as the planet approaches its star. As the orbital distance decreases, tidal forces will intensify exponentially, eventually overcoming the planet's structural integrity and causing it to break apart into a ring of debris orbiting the star. This process, known as tidal disruption, represents one of the most violent forms of planetary death imaginable. The planet won't simply crash into its star like a cosmic collision. Instead, it will be gradually shredded by tidal forces, with chunks of planetary material spiraling inward to form an accretion disk around the star. The disruption process will begin with the loss of the planet's outer atmospheric layers, stripped away by tidal forces and stellar radiation. As the planet moves closer to its star, deeper atmospheric layers will be peeled away, like the layers of an onion, revealing the dense interior structure beneath. Eventually, tidal forces will overcome the gravitational binding energy holding the planet's solid core together. At this point, the world will cease to exist as a coherent object and transform into a stream of rocky debris orbiting the star. The material will spiral inward, heating to incandescent temperatures as it falls toward the stellar surface. The final moments of WASP-18b's existence will create a spectacular light show visible from across the galaxy. As planetary debris rains down onto the star's surface, it will release enormous amounts of gravitational potential energy, causing the star to brighten temporarily as it consumes the remains of its former planetary companion. But WASP-18b's death spiral also provides astronomers with an unprecedented opportunity to study planetary destruction in real time. Unlike other forms of planetary death that operate over millions of years, the rapid orbital decay of this world allows scientists to observe measurable changes within human lifetimes. Precise measurements of WASP-18b's orbital period reveal subtle variations that provide clues about the planet's internal structure and the star's response to tidal forces. These observations allow astronomers to test theoretical models of tidal interaction and planetary disruption under the most extreme conditions imaginable. The study of WASP-18b has also revealed that tidal destruction operates as a precise physical process governed by well-understood gravitational dynamics. The planet's fate is sealed not by random cosmic accidents, but by the inexorable operation of physical laws that can be calculated with mathematical precision. This predictability transforms planetary destruction from a mysterious cosmic phenomenon into a calculable consequence of orbital mechanics. Given a planet's mass, orbital characteristics, and stellar properties, astronomers can determine with startling accuracy when and how the world will meet its end. Recent observations have detected additional planets in similar death spirals throughout the galaxy, suggesting that rapid tidal destruction represents a common fate for worlds that migrate too close to their stars. These discoveries reveal that the universe contains numerous examples of planets in their final death throes, each providing a glimpse into different stages of the destruction process. The comparative study of tidally disrupting planets has revealed the incredible diversity of destruction timescales operating throughout the galaxy. While WASP-18b faces annihilation in hundreds of thousands of years, other worlds experience even more rapid destruction, with some predicted to survive less than 100,000 years before tidal disruption. But perhaps the most disturbing aspect of studying planets in death spirals is the realization that their destruction is not only inevitable, but accelerating. As these worlds lose orbital energy and spiral inward, the tidal forces acting on them intensify, creating a runaway process that leads to exponentially increasing destruction rates. This acceleration means that planets like WASP-18b will spend most of their remaining lifetime in relatively stable orbits before experiencing rapid, catastrophic destruction in their final few thousand years. The transition from stable planet to debris disk will occur with shocking suddenness after hundreds of thousands of years of gradual orbital decay. The fate of WASP-18b serves as a cosmic memento mori, a reminder that even the most massive and stable-seeming worlds are temporary features in the universe's grand design. The planet's rapid destruction timeline forces us to confront the ultimate impermanence of planetary systems and the dynamic nature of cosmic evolution. Temperature measurements across WASP-18b's surface reveal the extreme thermal gradients created by tidal heating and stellar irradiation. The substellar point, the location on the planet's surface closest to the star, experiences temperatures exceeding 5,000 degrees Fahrenheit, while the planet's poles remain several hundred degrees cooler despite still being hot enough to melt lead. These temperature variations drive atmospheric circulation patterns of unprecedented violence, creating wind systems that redistribute heat and material around the planet at supersonic velocities. The atmospheric dynamics of WASP-18b represent weather patterns scaled up to planetary dimensions, where storm systems span entire hemispheres and persist for geological timescales. The chemical composition of WASP-18b's atmosphere reveals the exotic processes operating under extreme tidal heating. Spectroscopic analysis has detected vaporized metals including iron, magnesium, and titanium existing as gaseous components of the atmosphere. These elements, which form solid minerals under normal conditions, have been transformed into atmospheric constituents by the planet's extreme thermal environment. Advanced atmospheric models suggest that WASP-18b experiences chemical weather patterns where different metals condense and evaporate as atmospheric conditions vary with orbital position and tidal heating cycles. This creates a dynamic atmospheric chemistry that changes continuously as the planet undergoes its death spiral. The magnetic field environment around WASP-18b adds another layer of complexity to the planet's destruction process. The interaction between the planet's magnetic field and the stellar magnetic field creates complex electromagnetic effects that can influence atmospheric escape rates and tidal heating efficiency. Recent studies have detected magnetic field reconnection events between WASP-18b and its star, sudden releases of magnetic energy that accelerate charged particles to high velocities and contribute to atmospheric stripping. These magnetic interactions represent an additional destruction mechanism operating alongside tidal forces and thermal effects. The study of magnetically active planets in death spirals has revealed that electromagnetic effects can significantly alter the timeline and mechanism of planetary destruction. Planets with strong magnetic fields may experience different destruction pathways compared to non-magnetic worlds, adding yet another variable to the complex physics of planetary death. As WASP-18b continues its inexorable spiral toward destruction, it serves as a natural laboratory for studying matter under the most extreme gravitational and thermal conditions possible. The planet's surface experiences gravitational fields and temperature gradients that cannot be replicated in any terrestrial laboratory, providing unique insights into physics operating at the limits of what matter can endure. The pressure conditions within WASP-18b's interior, created by the combination of planetary gravity and tidal compression, generate exotic states of matter that may not exist anywhere else in the universe. These extreme pressure regimes could create crystalline structures and phase transitions that reveal new aspects of condensed matter physics. But beyond its scientific value, WASP-18b represents something more profound. A world whose destruction we can witness in real time. Unlike the gradual atmospheric stripping of evaporating planets or the ancient destruction that created exposed planetary cores, WASP-18b's death spiral operates on timescales that allow human observation of measurable change. This observability transforms abstract theoretical predictions into concrete observational reality. Astronomers can watch as this world approaches its doom, measuring the precise rate of orbital decay and comparing observations with theoretical models of tidal destruction. WASP-18b becomes a cosmic test case for our understanding of planetary physics under the most extreme conditions imaginable. The psychological impact of observing a world in its final death throes cannot be understated. WASP-18b forces us to confront the reality that planets, like all cosmic structures, are temporary arrangements of matter subject to the fundamental forces that govern the universe. The world's rapid approach to destruction serves as a stark reminder of the dynamic and often violent nature of cosmic evolution. Yet, even as WASP-18b spirals toward annihilation, its destruction will contribute to the ongoing cycle of cosmic creation and destruction. The material from the disrupted planet will be incorporated into the star, potentially affecting stellar evolution and the formation of future planetary systems. The atoms that once comprised solid ground and gaseous atmosphere will continue their cosmic journey, eventually finding their way into new worlds and new configurations of matter. This cosmic recycling process reveals the fundamental interconnectedness of all matter in the universe. The destruction of WASP-18b represents not an ending, but a transformation, as planetary material returns to the stellar environment from which it originally formed billions of years ago. As our exploration of the scariest exoplanets too hot to handle draws toward its conclusion, WASP-18b stands as the ultimate expression of planetary mortality. This world's measurable approach to destruction provides a cosmic countdown timer marking the final moments of a planet's existence. A reminder that even in the vast scales of space and time, some processes operate with the precision and inevitability of clockwork. The thermal extremes, atmospheric violence, and gravitational destruction we have witnessed throughout this journey represent just a fraction of the cosmic forces operating throughout the universe. From molecular furnaces that tear apart the building blocks of chemistry to gravitational death spirals that operate with mathematical precision, these worlds reveal the incredible diversity of destruction mechanisms that shape planetary evolution on cosmic scales. But perhaps the most remarkable aspect of these extreme worlds is not their destruction, but their existence. The fact that planets can survive, even temporarily, under such hostile conditions demonstrates the remarkable resilience of matter and the incredible range of environments where planetary systems can form and evolve. These thermal nightmares, violent as they are, expand our understanding of what constitutes a habitable universe and challenge our preconceptions about the limits of planetary existence. In pushing the boundaries of temperature, pressure, and gravitational force, these worlds reveal physics operating at extremes that illuminate the fundamental laws governing matter and energy throughout the cosmos. As we continue to discover new worlds throughout the galaxy, the lessons learned from these extreme planets will guide our understanding of planetary formation, evolution, and destruction. Each new discovery adds another chapter to the cosmic story of worlds that exist at the very limits of what the universe allows, pushing the boundaries between existence and annihilation in ways that continue to surprise and terrify us. The scariest exoplanets too hot to handle serve as reminders that the universe contains phenomena operating at scales and intensities that dwarf human experience. These worlds exist in thermal regimes more extreme than most stars, under gravitational forces that reshape matter itself, and in atmospheric conditions where the normal rules of chemistry and physics break down completely. Yet, in their very extremeness, these planets reveal the incredible creativity and violence of cosmic processes. They demonstrate that the universe is capable of creating conditions so extreme they seem impossible, yet operate according to physical laws we can understand and predict. In witnessing their destruction, we observe some of the most fundamental processes that govern the evolution of matter and energy throughout the cosmos. The journey through these thermal hells has revealed that planetary death, like planetary birth, operates through a diverse array of mechanisms, each more spectacular and violent than the last. From atmospheric stripping to tidal disruption, from molecular dissociation to gravitational consumption, the universe has developed numerous methods for dismantling the worlds it creates. But even as we witness these cosmic destructions, we must remember that they represent just one aspect of planetary evolution. For every world being destroyed by thermal extremes, countless others are forming in the cooler regions of stellar systems, beginning their own journeys through the complex dance of cosmic forces that will determine their ultimate fates. The scariest exoplanets, too hot to handle, remind us that we live in a universe of incredible violence and beauty, where creation and destruction operate hand in hand to shape the cosmic landscape. These worlds, terrifying as they are, represent the universe's capacity for creating conditions that push matter to its absolute limits while still maintaining the complex structures we call planets. In the end, these thermal nightmares serve as both warnings and wonders, revealing the incredible range of conditions under which planets can exist while simultaneously demonstrating the ultimate fragility of all cosmic structures. They are monuments to the power of stellar radiation, gravitational forces, and atmospheric dynamics operating at scales that challenge human comprehension. As we look up at the night sky, knowing that somewhere among those distant stars burn worlds where iron falls as rain, where molecules are torn apart and reformed in endless cycles of destruction, and where entire planets spiral toward their doom in gravitational death dances, we gain a deeper appreciation for the remarkable stability and gentleness of our own cosmic home. The scariest exoplanets, too hot to handle, exist as extreme outliers in the cosmic distribution of worlds, occupying the furthest reaches of what physics allows, while serving as natural laboratories for studying matter under conditions impossible to replicate on Earth. They are the universe's own extreme experiments, pushing the boundaries of planetary science into realms where astronomy and physics merge into a single discipline devoted to understanding matter at its absolute limits. These worlds will continue to burn and die in their thermal extremes long after human civilization has passed into cosmic history, serving as eternal reminders of the incredible forces that shape planetary evolution throughout the galaxy. They are cosmic beacons of destruction, marking the boundaries between existence and annihilation in the vast theater of space where the drama of planetary birth and death plays out across billions of years and countless worlds. In the depths of space, 150 light-years from Earth, there exists a phenomenon so bizarre that it challenges our fundamental understanding of planetary physics. Here, in a realm where normal chemistry breaks down completely, we encounter worlds where the very building blocks of matter undergo transformations that seem to violate the laws of nature itself. Welcome to the domain of quantum planetary destruction, where worlds don't simply die from heat or gravitational forces, but face annihilation at the subatomic level. These are planets where the extreme conditions create matter in states that exist nowhere else in the universe. Worlds where the boundary between chemistry and nuclear physics dissolves into cosmic horror. At the heart of this quantum nightmare lies WASP-121b, a world so hot that it has transcended the normal limits of planetary existence. With atmospheric temperatures exceeding 4,600 degrees Fahrenheit on its night side and over 5,000 degrees on its day side, this planet has entered a thermal regime where atoms themselves begin to break apart. But WASP-121b's true horror lies not in its temperature alone, but in what that temperature does to matter at the quantum level. The thermal energy is so intense that it strips electrons from their atomic orbits, creating a planetary atmosphere composed entirely of plasma. This isn't just a hot gas, but matter in its fourth state, where the fundamental electrical neutrality of atoms has been destroyed. In this plasma atmosphere, free electrons race through clouds of ionized nuclei at velocities approaching significant fractions of the speed of light. The electromagnetic fields generated by this charged particle soup create conditions that would make the interior of a nuclear reactor seem calm by comparison. Lightning, if it exists on this world, would arc between plasma clouds at voltages exceeding millions of volts. The plasma state of WASP-121b's atmosphere creates chemical processes that operate more like particle physics than traditional chemistry. When atomic nuclei stripped of their electrons collide in this superheated environment, they can undergo fusion reactions typically found only in stellar cores. The planet has become a distributed nuclear reactor, with fusion occurring randomly throughout its atmospheric volume. These atmospheric fusion events release bursts of high-energy radiation that further ionize the surrounding material, creating a cascading effect where nuclear reactions trigger additional nuclear reactions. The planet exists in a constant state of controlled nuclear explosion, held together only by its gravitational field and the delicate balance between thermal expansion and gravitational collapse. Spectroscopic observations of WASP-121b have detected the signatures of elements that shouldn't exist in planetary atmospheres. The extreme conditions have created isotopes typically found only in the hearts of dying stars or the aftermath of supernova explosions. These exotic nuclei exist for mere microseconds before decaying into more stable forms, but their presence reveals the incredible nuclear chemistry operating in this plasma hell. The magnetic field environment around WASP-121b adds another layer of quantum horror to its already nightmarish conditions. The movement of charged particles in the plasma atmosphere generates magnetic fields billions of times stronger than Earth's protective magnetosphere. These fields become so intense they begin to affect the vacuum of space itself, creating what physicists call quantum electrodynamic effects. In regions where the magnetic field strength exceeds critical thresholds, the quantum vacuum becomes polarized, splitting virtual particle pairs and creating real matter from apparently empty space. The planet's magnetic field has become so powerful that it literally manufactures particles from nothingness, adding mass to its atmosphere through pure electromagnetic force. But perhaps the most terrifying aspect of WASP-121d is the discovery that its extreme conditions are creating matter in what physicists call degenerate states. In certain regions of the planet's atmosphere, electrons have been compressed to densities where they form what's known as an electron-degenerate gas, a state of matter typically found only in white dwarf stars. This electron degeneracy creates pressure effects that operate independently of temperature, supporting atmospheric layers through quantum mechanical forces rather than thermal expansion. Entire regions of the planet's atmosphere exist in states where matter behaves according to quantum statistics rather than classical physics, creating atmospheric dynamics that follow the bizarre rules of quantum mechanics. The planet's core, subjected to the immense pressures generated by its plasma atmosphere and quantum degenerate layers, may have undergone phase transitions that create exotic forms of matter unknown anywhere else in the universe. Computer simulations suggest that the central pressure and temperature conditions could compress normal atomic matter into quark-gluon plasma, the same state that existed in the first microseconds after the Big Bang. If these simulations are correct, WASP-121b contains a core where protons and neutrons have been broken down into their constituent quarks, creating matter that exists in a state of pure quantum chromodynamic force. The planet has become a cosmic laboratory for recreating the conditions that existed when the universe itself was younger than a single atomic vibration. The study of quantum degenerate planets like WASP-121b has revealed that extreme thermal conditions can push matter through phase transitions that create entirely new states of existence. These worlds serve as natural particle accelerators, generating energies and pressures that exceed anything achievable in terrestrial laboratories by factors of millions. Recent observations have detected temporal variations in WASP-121b's quantum signatures, suggesting that the exotic matter states in its atmosphere and core undergo cyclic changes as the planet orbits its star. These quantum weather patterns operate on timescales measured in hours, rather than the geological epochs typical of normal planetary processes. The implications of quantum planetary destruction extend far beyond individual worlds to fundamental questions about the nature of matter itself. If planets can create and sustain exotic matter states under extreme conditions, what does this reveal about the universe's capacity for generating complexity through destruction? The discovery of quantum degenerate planets has also raised disturbing questions about the ultimate fate of matter in the universe. These worlds demonstrate that extreme conditions can push matter through phase transitions that fundamentally alter its properties, suggesting that the familiar atomic matter that makes up our everyday world may be just one of many possible states that matter can achieve. But WASP 121b represents just the most extreme example of quantum planetary destruction. Throughout the galaxy, astronomers have identified dozens of worlds where thermal conditions create exotic matter states that blur the boundaries between planetary science and particle physics. HD 149026b, located 256 light-years from Earth, has developed atmospheric conditions so extreme that they create what physicists call a Bose-Einstein condensate in its upper atmosphere. This quantum state, where particles lose their individual identities and behave as a single quantum entity, creates atmospheric layers that respond to gravitational and electromagnetic forces in ways that violate classical physics. The Bose-Einstein condensate layers in HD 149026b's atmosphere create optical effects that make the planet appear to flicker and pulse when observed from Earth. The quantum coherence of these atmospheric regions causes them to act like cosmic lasers, amplifying certain wavelengths of light while completely absorbing others. These quantum optical effects create atmospheric phenomena that exist nowhere else in the known universe. The planet's clouds, if they can still be called clouds, consist of quantum coherent matter that maintains phase relationships across thousands of miles of atmospheric volume. Weather patterns on this world operate according to quantum mechanical principles rather than classical fluid dynamics. The discovery of planets with quantum coherent atmospheres has forced astronomers to completely reconsider their models of atmospheric physics under extreme conditions. These worlds demonstrate that planetary atmospheres can maintain quantum mechanical properties on macroscopic scales, creating weather systems that follow the probabilistic rules of quantum mechanics rather than the deterministic laws of classical physics. Temperature measurements across HD 149026b reveal that the quantum condensate layers maintain perfect thermal equilibrium despite spanning enormous volumes of space. This quantum thermalization occurs through mechanisms that operate faster than the speed of light, suggesting that quantum entanglement effects play a role in atmospheric heat transport. The quantum entanglement of atmospheric particles on HD 149026b creates what physicists call non-local thermal effects, where changes in temperature in one region of the atmosphere instantaneously affect temperatures in distant regions without any apparent mechanism for energy transfer. The planet's atmosphere has become a macroscopic quantum system where the normal concepts of locality and causality break down. But the quantum horrors don't end with individual planets. Recent discoveries have revealed entire planetary systems where quantum effects operate on scales that encompass multiple worlds. In the Kepler-36 system, two planets orbit so close to each other that their atmospheric quantum fields interact directly, creating entangled atmospheric states that span interplanetary distances. When one planet in this quantum-entangled pair experiences atmospheric changes, the other planet's atmosphere responds instantaneously, regardless of the distance between them. The two worlds have become components of a single quantum system, their atmospheric evolution locked together by quantum mechanical forces that operate beyond the reach of classical physics. The study of quantum-entangled planetary systems has revealed that extreme thermal conditions can create coherent quantum states that persist across astronomical distances. These systems challenge our understanding of where quantum mechanics ends and classical physics begins, suggesting that the quantum realm may extend far beyond the atomic scales where we typically encounter it. Advanced theoretical models predict that quantum planetary destruction could lead to even more exotic phenomena. Under certain extreme conditions, the quantum field surrounding ultra-hot planets could undergo phase transitions that create cosmic strings, one-dimensional defects in space-time itself, that stretch across interstellar distances. These planetary cosmic strings would represent the ultimate expression of quantum destruction, where the extreme conditions on a single world create distortions in the fabric of space-time that affect the structure of reality itself. The planet would become not just a destroyer of matter, but a cosmic architect reshaping the geometry of space and time. Laboratory experiments designed to test these theoretical predictions have confirmed that extreme electromagnetic fields can indeed create measurable distortions in space-time, lending credibility to the possibility that quantum-degenerate planets might generate cosmic strings through their extreme field environments. The implications of space-time distortion around ultra-hot planets extend to fundamental questions about the nature of gravity and the structure of the universe. If planetary-scale quantum effects can influence space-time geometry, what does this reveal about the relationship between matter, energy, and the cosmic framework that contains them? Recent observations using gravitational wave detectors have identified signals that might originate from quantum planetary destruction events, suggesting that the extreme processes operating on these worlds create ripples in space-time that can be detected across galactic distances. These quantum gravitational waves carry information about matter states that exist nowhere else in the universe. The detection of quantum gravitational waves from planetary destruction represents a new frontier in both astronomy and fundamental physics. These signals provide direct evidence of quantum mechanical processes operating on planetary scales, confirming theoretical predictions about the behavior of matter under the most extreme conditions imaginable. But perhaps the most profound implication of quantum planetary destruction is what it reveals about the universe's capacity for creating complexity through extreme processes. These worlds demonstrate that even the most violent and destructive cosmic forces can generate new forms of organization and structure that expand our understanding of what's possible in the physical universe. The exotic matter states created in quantum-degenerate planets may represent the universe's method for exploring the full range of possibilities allowed by the laws of physics. Each world becomes a cosmic experiment, testing the limits of matter and energy under conditions that push the boundaries of existence itself. As we continue to discover more quantum-degenerate planets throughout the galaxy, we're uncovering a universe far stranger and more complex than previously imagined. These worlds exist at the intersection of planetary science, particle physics, and quantum mechanics, creating natural laboratories where the most fundamental laws of physics operate under conditions impossible to replicate on Earth. The study of quantum planetary destruction has also revealed the incredible interconnectedness of physical processes across vastly different scales. The same quantum mechanical principles that govern atomic behavior also operate in planetary atmospheres under extreme conditions, suggesting a deep unity in the laws that govern matter from the smallest to the largest scales. But quantum-degenerate planets also serve as harbingers of even more extreme phenomena that may exist in the cosmic deep. If planets can create exotic matter states and space-time distortions, what other impossible conditions might exist in the universe's most extreme environments? The answer may lie in the discovery of worlds that have transcended the normal boundaries of planetary existence entirely, entering realms where the distinction between matter and energy, between space and time, becomes meaningless. These are planets that have undergone transformation so complete that they challenge our very definition of what constitutes a world. In the outer reaches of the galaxy, where stellar evolution has progressed beyond the normal main sequence, astronomers have detected signals that suggest the existence of planets composed entirely of dark matter, worlds invisible to normal observation but detectable through their gravitational effects on surrounding space. These dark matter planets, if they exist, would represent the ultimate expression of exotic planetary evolution. Composed of particles that interact only through gravitational force, they would exist as ghostly worlds occupying the same space as normal matter while remaining completely invisible to electromagnetic observation. The gravitational signatures of dark matter planets reveal worlds with masses exceeding Jupiter, but with gravitational effects that suggest densities far below what normal matter could achieve. These planets exist in a state of gravitational coherence maintained by forces we don't fully understand, creating stable structures from matter that barely interacts with itself. Recent theoretical work suggests that dark matter planets could develop internal structures and dynamics as complex as normal worlds, despite being composed of particles that seem incapable of forming solid structures. The gravitational self-interaction of dark matter under extreme densities might create phase transitions that generate exotic forms of organization and complexity. If dark matter planets exist, they would represent a parallel universe of planetary evolution operating according to principles we're only beginning to understand. These invisible worlds might populate every stellar system in the galaxy, creating a hidden cosmic ecosystem that remains completely undetectable to normal observation. The search for dark matter planets has pushed observational astronomy to its limits, requiring the detection of gravitational effects so subtle they can barely be distinguished from instrumental noise. But the potential discovery of these invisible worlds would revolutionize our understanding of planetary formation and the nature of matter itself. As our journey through the scariest exoplanets too hot to handle reaches toward its ultimate extremes, we encounter phenomena that transcend the normal categories of planetary science. From molecular furnaces that tear apart chemistry itself to quantum degenerate worlds where matter exists in states found nowhere else in the universe, we have witnessed the incredible diversity of destruction and transformation that operates throughout the cosmic deep. These thermal nightmares reveal a universe far more violent and creative than our earthly experience suggests. They demonstrate that the gentle, life-supporting conditions we enjoy on Earth represent a narrow oasis of stability in a cosmos dominated by forces operating at extremes that challenge the very foundations of physical law. But in their extremeness, these worlds also reveal the incredible resilience and adaptability of matter itself. The fact that planets can exist and maintain complex structures under such hostile conditions suggests that the universe is capable of creating and sustaining organization under circumstances that seem impossible from our limited perspective. The scariest exoplanets too hot to handle serve as cosmic laboratories where the fundamental laws of physics are tested under conditions that reveal new aspects of reality. They expand our understanding of what's possible in the universe while simultaneously humbling us with demonstrations of forces that dwarf human comprehension. As we continue to explore the cosmos and discover new worlds that push the boundaries of planetary existence, we're uncovering a universe of incredible complexity and beauty, where even the most violent and destructive processes can create phenomena of stunning intricacy and elegance. These thermal monsters, quantum nightmares, and invisible worlds remind us that we live in a universe of infinite possibility, where the laws of physics operate across scales and in regimes that continue to surprise and inspire us. They are monuments to the universe's capacity for creating the impossible, transforming destruction into new forms of creation that illuminate the deepest mysteries of existence itself. The journey through these cosmic hells has revealed that planetary death, like planetary birth, operates through mechanisms of breathtaking complexity and violence. From the molecular dissociation furnaces of Kelt 9b to the quantum degenerate plasma atmospheres of WASP 121b, from the gravitational death spirals of WASP 18b to the invisible dark matter worlds that may populate every corner of the galaxy, we have witnessed destruction elevated to an art form. Yet even as these worlds face annihilation through processes that challenge our understanding of physics itself, they continue to teach us about the nature of matter, energy, and the cosmic forces that shape the universe. In their final moments, as they undergo transformations that push the boundaries of existence, they reveal new aspects of reality that expand our comprehension of what's possible in the vast theater of space and time. The scariest exoplanets too hot to handle exist as extremes in the cosmic distribution of worlds, occupying the furthest reaches of what physics allows, while serving as natural laboratories for studying matter under conditions that cannot be replicated anywhere else. They are the universe's own experiments in extreme physics, pushing the boundaries of planetary science into realms where the normal rules break down and new forms of organization emerge from chaos. These worlds will continue their dance of destruction and transformation long after human civilization has passed into cosmic memory, serving as eternal reminders of the incredible forces that operate throughout the galaxy. They are beacons of extremity, marking the boundaries between existence and annihilation in the vast cosmic ocean where the drama of planetary evolution plays out across billions of years and countless worlds, each one a unique experiment in the physics of matter pushed to its absolute limits. Deep within the cosmic furnace of stellar creation, where temperatures exceed 100 million degrees and nuclear fusion transforms hydrogen into the heavier elements that form the building blocks of worlds, we find the origins of the most terrifying planetary destruction mechanisms in the universe. These are not the gentle stellar nurseries depicted in astronomy textbooks, but violent cosmic foundries where the seeds of planetary annihilation are forged in nuclear fire. The story begins in the hearts of massive stars, stellar giants containing 20 to 50 times the mass of our Sun. These stellar monsters burn through their nuclear fuel at rates that would consume our Sun's entire energy reserves in just a few million years. As they exhaust successive layers of nuclear fuel, they create the heavy elements that will eventually find their way into planetary atmospheres billions of years later. But the nuclear processes that create these elements also doom them to become instruments of planetary destruction. Iron, nickel, titanium, and other metals forged in stellar cores carry within their atomic structure the capacity to absorb and emit radiation in ways that can destabilize entire planetary atmospheres under extreme conditions. When these stellar-forged elements are incorporated into planetary atmospheres on ultra-hot worlds, they create what astronomers call opacity crises. The metallic atoms absorb stellar radiation so efficiently that they heat the surrounding atmospheric gases to temperatures that trigger runaway greenhouse effects. The very elements that make terrestrial worlds possible become atmospheric poisons when subjected to the intense radiation fields around close-orbiting planets. This stellar heritage of destruction explains why the most extreme exoplanets share common characteristics despite forming around different types of stars. The heavy elements in their atmospheres were all forged in similar stellar environments, carrying identical destructive potential that manifests when exposed to intense stellar radiation. Recent observations have revealed that the stellar formation process itself determines which types of planets will face thermal destruction. Stars that form in metal-rich environments create planetary systems where heavy elements are abundant from the beginning of planetary formation. These systems are predisposed to developing ultra-hot planets with metallic atmospheres that become unstable under stellar heating. Conversely, stars that form in metal-poor regions of the galaxy create planetary systems with different atmospheric compositions that may be more resistant to thermal destruction. The metallicity of the stellar nursery where a star forms determines the ultimate fate of any planets that develop around it billions of years later. This connection between stellar formation and planetary destruction reveals the incredible timescales over which cosmic processes operate. The nuclear reactions that occurred in massive stars billions of years ago continue to influence planetary evolution today, creating a web of cause and effect that spans the entire history of the galaxy. Advanced stellar evolution models predict that the most extreme planetary destruction events are yet to come. As the galaxy ages and successive generations of massive stars enrich the interstellar medium with heavy elements, future planetary systems will form with even higher metallicities. These metal-rich worlds will be even more vulnerable to thermal destruction than the extreme planets we observe today. The future galaxy may be populated with planets that exist in perpetual states of thermal crisis, worlds where the abundance of stellar-forged heavy elements creates atmospheric conditions so unstable that planetary survival becomes impossible. These future thermal nightmares will make today's ultra-hot Jupiters seem temperate by comparison. But stellar nucleosynthesis creates more than just the raw materials for planetary destruction. The nuclear processes operating in stellar cores also determine the types of radiation that stars emit, directly influencing the thermal environments around their planets. Stars with different nuclear burning phases emit radiation at different wavelengths and intensities, creating unique destruction signatures for planets orbiting different stellar types. The discovery of planets around evolved stars has revealed entirely new categories of thermal destruction. Red giant stars, which have exhausted their core hydrogen and expanded to enormous sizes, create radiation environments that can strip atmospheres from planets at distances that would be safe around main sequence stars. These evolved stellar systems host planets experiencing thermal destruction through mechanisms that operate on accelerated timescales. As red giant stars continue to expand, they can engulf planets that once orbited safely in their stellar systems. The planetary destruction occurs not through gradual atmospheric stripping, but through direct immersion in stellar material. Planets that survive the red giant phase face an even more terrifying fate. When the star eventually sheds its outer layers and becomes a white dwarf, any remaining planets experience sudden changes in their radiation environment that can trigger catastrophic atmospheric collapse or explosive atmospheric expansion. The white dwarf phase creates thermal conditions around surviving planets that oscillate between extremes as the stellar remnant cools over geological timescales. Planets in these systems experience thermal cycling that subjects them to repeated heating and cooling episodes, each capable of fundamentally altering atmospheric chemistry and structure. Some planets around white dwarf stars have been observed to develop atmospheric compositions that change dramatically over periods of just a few thousand years, transforming from hydrogen-rich to metal-rich atmospheres as different layers of the planetary interior are exposed to the varying radiation environment. These rapid atmospheric transformations create planets that exist in states of perpetual chemical revolution, where atmospheric composition undergoes continuous changes that prevent the establishment of stable climate systems. The worlds become laboratories for studying atmospheric chemistry under conditions of constant flux. But perhaps the most extreme stellar environments are found around neutron stars, the ultra-dense remnants of massive stellar explosions. Planets that somehow survive supernova explosions and remain in orbit around neutron stars face radiation environments so intense they challenge the basic physics of atmospheric survival. Neutron star radiation includes not just electromagnetic energy, but also high-energy particle beams that can penetrate deep into planetary interiors. Planets in these systems experience irradiation that transforms their internal structure, converting normal atomic matter into exotic forms that exist nowhere else in the universe. The magnetic fields around neutron stars create additional hazards for any surviving planets. These fields, billions of times stronger than Earth's magnetic field, can induce electrical currents in planetary materials, strong enough to melt solid rock and vaporize metallic cores. Recent observations have detected planets around pulsars, rapidly rotating neutron stars that emit beams of radiation like cosmic lighthouses. These pulsar planets experience radiation doses that vary dramatically as the neutron star rotates, creating thermal cycling that subjects them to temperature swings of thousands of degrees within hours. The discovery of pulsar planets has revealed that planetary systems can survive even the most catastrophic stellar explosions. But the worlds that emerge from these cosmic disasters bear little resemblance to normal planets. They exist as radiation-blasted remnants, stripped of their original atmospheres and subjected to constant bombardment by high-energy particles. These post-supernova planets serve as cosmic archaeological sites, preserving evidence of the most violent stellar explosions while simultaneously demonstrating the incredible resilience of planetary systems under extreme conditions. They are survivors of cosmic catastrophes that destroyed their parent stars, yet they continue to orbit the stellar remnants in defiance of the forces that should have obliterated them. The study of planets around evolved stars has also revealed that stellar death can create new opportunities for planetary formation. The heavy elements expelled during stellar explosions can condense into new generations of planets around the stellar remnants, creating worlds with compositions unlike anything that formed during the star's main sequence lifetime. These second-generation planets inherit the extreme chemical legacies of stellar death, forming with atmospheric compositions dominated by the exotic isotopes created during supernova nucleosynthesis. They represent entirely new categories of worlds that exist only in post-stellar environments. Temperature measurements of second-generation planets reveal atmospheric chemistries operating with isotopes that decay over geological timescales, creating worlds where radioactive heating contributes significantly to surface temperatures. These planets warm themselves through nuclear decay processes inherited from their stellar formation environment. The radioactive heating creates thermal conditions that remain stable for millions of years, providing energy sources independent of stellar radiation. But as the radioactive isotopes decay, these worlds face gradual cooling that will eventually transform them into frozen remnants of stellar death. Advanced models of stellar evolution predict that the galaxy's future will be dominated by these post-stellar planetary systems, worlds orbiting white dwarfs, neutron stars, and black holes in environments where normal stellar heating is absent. These future planets will depend entirely on internal energy sources for their thermal evolution. The transition from stellar-heated to internally heated planetary systems represents one of the most fundamental changes in cosmic evolution. As main sequence stars exhaust their nuclear fuel and die, the galaxy will become populated with planets that exist in perpetual darkness, warmed only by the fading heat of their formation and the decay of radioactive elements. But even in these dark future environments, thermal destruction will continue to operate through new mechanisms. Tidal heating from compact stellar remnants will subject planets to gravitational forces that create internal friction and thermal generation. The galaxy's future may be filled with worlds that burn from within while orbiting in the darkness around stellar corpses. The ultimate expression of stellar influence on planetary destruction may be found around black holes, where the gravitational fields become so intense they distort space-time itself. Planets orbiting close to black holes experience not just tidal forces, but relativistic effects that alter the passage of time and the nature of the thermal processes. Time dilation around black holes means that thermal destruction processes that would take millions of years in normal spacetime can be compressed into much shorter periods as measured by external observers. Planets spiraling toward black holes experience accelerated destruction timelines where their final moments are stretched across cosmic time. The event horizons of black holes represent the ultimate boundary for planetary existence. Any world that crosses this threshold ceases to exist in the normal sense, its matter and energy becoming part of the black hole's mass while its information content becomes encoded on the event horizon surface. Recent theoretical work suggests that the information content of destroyed planets may be preserved in the quantum fluctuations around black hole event horizons, creating a form of planetary immortality where the essential characteristics of destroyed worlds persist as quantum information even after their physical destruction. These quantum archaeological records of planetary destruction could theoretically be recovered through the Hawking radiation emitted by evaporating black holes, providing future civilizations with detailed information about worlds that were destroyed billions of years earlier. But the timescales involved in black hole evaporation exceed the current age of the universe by factors of billions, meaning that any information recovery would occur in a cosmic future so distant that the galaxy itself will have evolved beyond recognition. The study of planetary destruction around compact objects has revealed that thermal death represents just one pathway among many for planetary annihilation. Gravitational destruction, electromagnetic destruction, and quantum mechanical destruction all operate simultaneously in these extreme environments, creating destruction mechanisms that transcend simple thermal processes. As our understanding of these extreme destruction mechanisms continues to evolve, we're discovering that the boundary between planetary science and fundamental physics becomes increasingly blurred. The most extreme planetary environments serve as natural laboratories for testing the limits of physical law under conditions that cannot be replicated anywhere else. The thermal nightmares we have explored throughout this journey represent just a fraction of the destruction mechanisms operating throughout the universe. From molecular dissociation furnaces to quantum degenerate plasma atmospheres, from gravitational death spirals to stellar consumption events, we have witnessed the incredible diversity of ways that planets can face annihilation. But perhaps the most profound lesson from studying these extreme worlds is that destruction and creation operate as complementary processes in cosmic evolution. The same forces that destroy planets also create the conditions for new forms of matter and energy to emerge, contributing to the ongoing evolution of complexity throughout the universe. The atoms that comprise our bodies were forged in stellar cores through the same nuclear processes that doom planets to thermal destruction when those elements are concentrated in extreme atmospheric environments. We are literally made from the ashes of stellar death, assembled into living forms that can contemplate the cosmic forces that created and will eventually destroy us. This cosmic perspective transforms our understanding of planetary destruction from a catalog of horrors into a profound meditation on the nature of existence itself. The extreme worlds we have encountered exist as temporary arrangements of matter and energy, subject to the same physical laws that govern all cosmic evolution. Their destruction serves as a reminder that all structures in the universe, from the smallest atoms to the largest galactic clusters, are temporary features in the ongoing cosmic story. Even the most stable and long-lived structures will eventually succumb to the fundamental forces that created them, contributing their constituent matter and energy to new cycles of creation and destruction. The scariest exoplanets, too hot to handle, exist as monuments to this cosmic impermanence. Worlds whose extreme conditions illuminate the boundaries between existence and annihilation. They are cosmic candles burning at both ends, consuming themselves in spectacular displays of thermal violence, while simultaneously revealing the fundamental physics that governs all matter and energy. As we continue to discover new worlds throughout the galaxy, each more extreme than the last, we're uncovering a universe of incredible creativity and violence, where the forces of creation and destruction operate on scales that challenge human comprehension. These thermal monsters serve as reminders that we inhabit a cosmos far stranger and more dynamic than our earthly experience suggests. The journey through these cosmic hells has revealed that planetary death represents one of the universe's most creative processes, transforming simple matter into exotic states that expand our understanding of what's possible under the laws of physics. In witnessing their destruction, we observe the universe's capacity for creating beauty through violence, order through chaos, and new forms of complexity through the systematic dismantling of existing structures. The scariest exoplanets too hot to handle will continue their dance of destruction long after human civilization has joined the cosmic cycle of creation and destruction. They are eternal reminders of the forces that shape the universe, burning in the darkness as beacons of extremity that mark the boundaries of what matter can endure, while still maintaining the complex organization we recognize as planetary existence. In the end, these thermal nightmares serve as both warning and wonder, revealing the incredible range of conditions under which planets can exist, while simultaneously demonstrating the ultimate fragility of all cosmic structures. They are the universe's own experiments in extreme physics, pushing matter to its absolute limits while creating natural laboratories where the fundamental laws of reality are tested under conditions that illuminate the deepest mysteries of existence itself. Beyond the realm of thermal annihilation lies something even more disturbing. Deep in the constellation Ursa Major, 500 light-years from Earth, astronomers have discovered a world that represents the ultimate expression of planetary vulnerability. This is a planet caught in a cosmic feedback loop so vicious that its own survival mechanisms have become instruments of accelerated destruction. TOI 2109b completes one orbit around its star in just 16 hours, making it one of the shortest orbital periods ever recorded. But this breakneck pace around its stellar host creates conditions so extreme that the planet exists in a state of perpetual crisis, where every attempt to maintain stability triggers even more violent instability. The physics governing TOI 2109b's death dance operate with a precision that would be mathematically elegant if it weren't so thoroughly catastrophic. As the planet races around its star at distances that make Mercury's orbit seem spacious, it experiences temperature variations that swing by thousands of degrees within hours. These thermal oscillations create atmospheric pressure waves that propagate around the planet like cosmic tsunamis. But the true horror of TOI 2109b lies in what astronomers call thermal runaway feedback. As the planet's atmosphere heats during its closest approach to the star, it expands dramatically, pushing atmospheric material closer to the Roche limit, where stellar gravity can strip it away. This atmospheric expansion makes the planet more vulnerable to mass loss, which reduces its gravitational field, which makes it even more susceptible to atmospheric stripping. The feedback loop creates a self-accelerating destruction process, where each orbital cycle leaves the planet slightly more vulnerable than the last. Computer models suggest that TOI 2109b is losing atmospheric mass at an exponentially increasing rate, with current projections indicating complete atmospheric loss within 40,000 years. 40,000 years represents mere moments in cosmic time, shorter than the period required for continents to drift appreciable distances on Earth. We are witnessing a world in its final death throes, experiencing planetary apocalypse compressed into timescales that approach human historical memory. The thermal oscillations on TOI 2109b create weather patterns that operate more like seismic events than atmospheric phenomena. As the planet swings between temperature extremes, its atmosphere undergoes phase transitions, where gases condense and vaporize in massive atmospheric avalanches that redistribute material across the entire planetary surface. These atmospheric avalanches carry enough energy to power human civilization for millions of years, yet they occur routinely as part of the planet's normal weather cycle. Imagine storms where the energy release exceeds that of nuclear weapons, occurring not as rare catastrophic events, but as regular features of daily atmospheric dynamics. The magnetic field environment around TOI 2109b adds another layer of destruction to its already nightmarish conditions. The planet's rapid orbital motion through its star's magnetic field generates electrical currents so intense they heat the planetary interior through electromagnetic induction. The planet literally cooks itself from within as it races through magnetic field lines. This electromagnetic heating creates internal temperature gradients that drive convection currents of molten rock through the planet's interior. The entire world has become a cosmic dynamo, converting orbital motion into thermal energy through electromagnetic processes that operate on planetary scales. But electromagnetic heating represents just one component of TOI 2109b's internal energy budget. The extreme tidal forces generated by its close stellar orbit create additional heating through gravitational compression and release. Each orbital cycle subjects the planet to tidal forces that squeeze and stretch its interior like a cosmic stress ball. The combination of electromagnetic and tidal heating creates internal temperatures that may exceed those found in the planet's atmosphere. TOI 2109b burns from within and without, heated by stellar radiation from above and internal friction from below. The planet exists in a state of thermal siege, surrounded by destruction mechanisms that attack from every direction. Recent observations have detected seismic activity on TOI 2109b that suggests the planet's solid interior is undergoing continuous restructuring due to thermal stress. The world experiences planetary earthquakes as its interior expands and contracts with each orbital cycle, creating fault systems that span entire hemispheres. These thermal earthquakes release energy comparable to the most powerful seismic events in Earth's geological history, but they occur hundreds of times per year as regular consequences of the planet's extreme thermal cycling. The world's surface, if it can still be called a surface, undergoes constant reconstruction through seismic violence. The atmospheric composition of TOI 2109b reveals the chemical signatures of a world consuming itself. Spectroscopic analysis has detected elements from the planet's interior mixed into its atmosphere, indicating that thermal stress has created volcanic activity so intense it breaches the planet's outer layers. This volcanism operates on scales that dwarf anything in our solar system. Entire continents' worth of molten rock are ejected into the atmosphere during each thermal cycle, only to rain back down as the planet cools during its orbital swing away from the star. The world experiences geological recycling compressed into timescales measured in hours rather than millions of years. But perhaps the most disturbing aspect of TOI 2109b is the discovery that its extreme conditions are creating new forms of matter that exist nowhere else in the universe. The combination of extreme temperature, pressure, and electromagnetic fields has compressed normal atomic matter into configurations that challenge our understanding of condensed matter physics. Deep within the planet's interior, where temperatures exceed 15,000 degrees Fahrenheit and pressures approach those found in stellar cores, normal atomic structure breaks down completely. Electrons are stripped from their atomic orbits and compressed into degenerate states where they form what physicists call an electron sea, a quantum fluid that flows through the planet's interior like liquid metal. This electron sea creates electrical conductivity so extreme that the planet's interior becomes essentially a single massive electrical conductor. Currents flow through the planetary volume, with resistance approaching zero, creating electromagnetic effects that influence the planet's interaction with its star's magnetic field. The planet has become a cosmic electrical circuit, with current flows that exceed the electrical output of entire civilizations. These planetary-scale electrical phenomena create magnetic fields so intense they affect the structure of nearby space, creating regions where normal electromagnetic physics operates according to modified rules. Advanced theoretical models suggest that the extreme electrical currents in TOI 2109b's interior may be approaching the threshold where electromagnetic effects begin to influence gravitational fields. The planet may be generating what physicists call electromagnetic gravity, a theoretical phenomenon where intense electromagnetic fields create measurable distortions in space-time. If electromagnetic gravity is indeed operating on TOI 2109b, the planet would represent the first observed example of a world where electromagnetism and gravity merge into a unified force field. The planet would exist in a state where the fundamental forces of nature operate according to principles that transcend our normal understanding of physics. The study of extreme electromagnetic planets like TOI 2109b has revealed that planetary destruction can operate through mechanisms that blur the boundaries between different branches of physics. These worlds serve as natural laboratories where electromagnetic, gravitational, and thermal processes combine to create destruction mechanisms that exist nowhere else in the universe. But TOI 2109b's electromagnetic nightmare is just one example of the exotic destruction processes operating throughout the galaxy. Other worlds face annihilation through mechanisms so bizarre they challenge our fundamental concepts of what constitutes planetary death. In the Kepler-70 system, astronomers have discovered planets orbiting a subdwarf star, the helium-burning remnant of a red giant that has shed its outer layers. These worlds, designated Kepler-70b and Kepler-70c, exist in thermal environments so extreme they have transcended normal planetary physics entirely. The subdwarf star burns at temperatures exceeding 50,000 degrees Fahrenheit, nearly 5 times hotter than our Sun's surface. This creates a radiation environment around the orbiting planets that subjects them to energy fluxes capable of vaporizing any known material instantly. Yet somehow, these worlds continue to exist as coherent objects despite being bathed in radiation that should destroy them completely. The survival of planets around subdwarf stars has forced astronomers to reconsider their understanding of what materials can exist under extreme radiation conditions. These worlds may be composed of exotic matter states that remain stable only under the intense energy bombardment they experience in their current orbits. Spectroscopic analysis of the Kepler-70 planets has detected atmospheric signatures that suggest the presence of elements in plasma states so highly ionized that individual atoms have been stripped of most of their electrons. The planetary atmospheres consist of bare atomic nuclei swimming in seas of free electrons, creating matter in states typically found only in stellar interiors. These plasma atmospheres exhibit properties that transcend normal gas dynamics. The highly ionized particles interact through electromagnetic forces rather than simple pressure and temperature effects, creating atmospheric circulation patterns that follow the laws of magnetohydrodynamics rather than conventional meteorology. The magnetic field interactions in these plasma atmospheres create phenomena that exist nowhere else in the known universe. Lightning, if it can still be called lightning, consists of magnetic field reconnection events that release energy equivalent to hydrogen bombs. Thunder propagates as magnetohydrodynamic shock waves that travel at significant fractions of the speed of light. Weather systems on these plasma worlds operate according to principles borrowed from stellar physics rather than planetary science. Atmospheric storms consist of magnetic flux tubes that twist and reconnect, creating energy releases that exceed the total power output of our Sun during their brief existence. The discovery of plasma planets has revealed that worlds can maintain structural integrity under radiation conditions previously thought to be instantly lethal. These planets demonstrate that matter can achieve stable configurations under circumstances that push the boundaries of what physicists considered possible for planetary-scale objects. But the plasma planets around subdwarf stars represent just one category of worlds that have transcended normal planetary physics through extreme radiation exposure. Throughout the galaxy, astronomers continue to discover planets that exist in radiation environments so intense they create entirely new categories of planetary phenomena. Recent observations have identified worlds orbiting white dwarf stars, where the intense ultraviolet radiation has ionized the planetary atmospheres to such extreme degrees that the atmospheric particles achieve relativistic velocities. These ultra-relativistic atmospheres create optical effects that make the planets appear to pulse and flicker as atmospheric particles approach significant fractions of the speed of light. The relativistic motion of atmospheric particles creates Doppler effects so extreme that different parts of the planet's atmosphere emit light at dramatically different wavelengths. The worlds appear to change color continuously, as relativistic atmospheric dynamics create shifting patterns of red and blue shifted emission. These relativistic atmospheric effects create observational challenges that push ground-based astronomy to its limits. The planets exist in states of constant spectroscopic flux, with their observable properties changing faster than telescopes can track. They represent moving targets in both the literal and observational sense. The study of relativistic planets has also revealed new forms of atmospheric chemistry operating under conditions where particle velocities approach the speed of light. Chemical reactions occur through relativistic collision processes that create exotic molecular configurations impossible under normal conditions. Some of these relativistic chemical processes produce molecular species that exist for mere nanoseconds before decaying into more stable forms. The atmospheric chemistry operates like a continuous particle physics experiment, creating and destroying exotic molecules at rates that exceed billions of reactions per second. The energy densities achieved in relativistic planetary atmospheres approach those found in particle accelerators, but distributed across planetary volumes rather than confined to laboratory beamlines. These worlds serve as natural cosmic ray generators, producing high-energy particles that propagate throughout their stellar systems. But perhaps the most extreme planetary destruction mechanism discovered to date operates on worlds that have undergone complete phase transitions from normal matter into exotic states that exist only under the most extreme conditions imaginable. These are planets that have transcended the normal boundaries between matter and energy, entering realms where the distinction becomes meaningless. Deep in the galactic core, where stellar densities exceed anything found in our local neighborhood, astronomers have detected gravitational signatures that suggest the existence of planets composed entirely of strange matter. These hypothetical worlds consist of quarks arranged in configurations that remain stable only under the extreme gravitational fields found near the galaxy's central black hole. Strange matter planets, if they exist, would represent the ultimate expression of exotic planetary evolution. Composed of quarks bound together by the strong nuclear force rather than electromagnetic interactions, they would exhibit properties unlike any normal matter. Their surfaces would be harder than diamond, yet more fluid than liquid mercury, creating landscapes that defy conventional description. The gravitational signatures of potential strange matter planets indicate objects with densities approaching those found in neutron star cores, but existing as free-floating worlds rather than stellar remnants. These planets would pack the mass of entire solar systems into volumes smaller than Earth, creating gravitational fields so intense they bend light into complex patterns around their surfaces. Recent theoretical work suggests that strange matter planets could form through the collision of neutron stars with normal planets, converting the ordinary matter into exotic quark configurations through sheer gravitational pressure. The collision process would destroy the original planet while simultaneously creating an entirely new form of world from its constituent matter. The study of exotic matter planets has pushed theoretical physics into realms where planetary science and particle physics merge into a unified discipline. These worlds exist at the intersection of astronomy, nuclear physics, and quantum chromodynamics, creating natural laboratories where the most fundamental forces of nature operate under conditions impossible to replicate on Earth. But strange matter planets may represent just the beginning of exotic planetary evolution. Advanced theoretical models predict the existence of worlds composed of dark matter, antimatter, and even more exotic forms of matter that challenge our understanding of what constitutes physical reality. Dark matter planets, composed of particles that interact only through gravitational force, would exist as invisible worlds occupying the same space as normal matter while remaining completely undetectable to electromagnetic observation. These ghost worlds might populate every stellar system in the galaxy, creating a hidden universe of planetary evolution operating according to principles we barely understand. The search for dark matter planets requires detecting gravitational effects so subtle they approach the limits of observational precision. But the potential discovery of these invisible worlds would revolutionize our understanding of planetary formation and the nature of matter itself. Antimatter planets represent an even more exotic possibility. Worlds composed of particles with opposite charge and spin properties compared to normal matter. These worlds would exist in perpetual danger of annihilation should they encounter any normal matter, creating planetary systems where survival depends on maintaining perfect isolation from the ordinary matter universe. The energy releases from matter-antimatter annihilation would make these worlds incredibly luminous, despite being composed of the universe's most dangerous form of matter. Antimatter planets would burn with their own annihilation light, creating cosmic beacons visible from across the galaxy, while simultaneously representing the most hazardous objects in the universe. Recent observations of high-energy gamma-ray bursts have detected signatures that might originate from antimatter planet annihilation events, suggesting that these exotic worlds might exist and occasionally encounter normal matter with catastrophic results. The gamma-ray signatures indicate energy releases that exceed anything produced by normal stellar processes. But perhaps the most profound implication of exotic matter planets is what they reveal about the universe's capacity for creating complexity through extreme processes. These worlds demonstrate that planetary evolution can transcend the normal boundaries of matter and energy, creating new forms of organization that expand our understanding of what's possible in the physical universe. The existence of exotic matter planets suggests that the universe contains forms of planetary evolution operating according to principles we haven't yet discovered. Each new category of extreme world reveals previously unknown aspects of cosmic physics, expanding our comprehension of the forces that shape matter and energy throughout the cosmos. As our technology advances and we develop new methods for detecting these exotic worlds, we may discover that the universe is populated with forms of planetary existence that transcend our current understanding of what constitutes a world. The cosmos may contain hierarchies of planetary evolution that operate according to principles we can barely imagine. The journey through the scariest exoplanets too hot to handle has revealed a universe far stranger and more violent than our earthly experience suggests. From molecular furnaces that tear apart chemistry itself to exotic matter worlds that challenge our understanding of physical reality, we have witnessed the incredible diversity of destruction and transformation that operates throughout the cosmic deep. These thermal nightmares exist as monuments to the universe's capacity for creating the impossible, while simultaneously demonstrating the ultimate fragility of all cosmic structures. They are laboratories where the fundamental laws of physics are tested under conditions that illuminate the deepest mysteries of existence, while revealing new aspects of reality that continue to surprise and humble us. But in their extremeness, these worlds also reveal the incredible resilience and creativity of cosmic evolution. The fact that planets can exist and maintain complex structures under such hostile conditions suggests that the universe is capable of creating and sustaining organization under circumstances that seem impossible from our limited perspective. The scariest exoplanets, too hot to handle, serve as cosmic teachers, expanding our understanding of what's possible while simultaneously reminding us that we inhabit a universe of infinite mystery and wonder. They are eternal flames burning in the darkness, marking the boundaries between existence and annihilation, while illuminating the path toward deeper understanding of the cosmic forces that shape all matter and energy throughout the vast theater of space and time. But the most chilling revelation comes from recent calculations showing that these extreme worlds are not random cosmic accidents. They represent the inevitable endpoints of planetary evolution under specific conditions, suggesting that somewhere among the billions of worlds in our galaxy, thermal destruction is unfolding at this very moment. As we speak, entire atmospheres are being stripped away, molecule by molecule, planets are spiraling towards stellar consumption, and worlds are undergoing transformations so complete they challenge our definition of what constitutes planetary existence. The mathematics of destruction operate with clockwork precision across the cosmos. Every ultra-hot Jupiter we've discovered follows predictable pathways toward annihilation, their fates sealed by the same physical laws that govern atomic interactions and stellar evolution. These worlds exist as cosmic proof that the universe contains destruction mechanisms operating on scales that dwarf human comprehension. Yet perhaps the most profound lesson from our journey through these thermal hells is what they reveal about the nature of existence itself. These planets, terrifying as they are, demonstrate that even under the most extreme conditions imaginable, complex structures can form and persist. They expand our understanding of where organization and complexity can emerge in a universe dominated by forces that seem designed for destruction. The scariest exoplanets, too hot to handle, serve as both warning and wonder, revealing the incredible range of conditions under which worlds can exist, while simultaneously demonstrating that all cosmic structures are temporary arrangements of matter and energy subject to the fundamental forces that govern reality. They are monuments to the universe's capacity for creating beauty through violence, order through chaos, and profound insights through the systematic exploration of cosmic extremes. These thermal nightmares will continue burning long after human civilization has joined the cosmic cycle of creation and destruction. They are eternal reminders that we inhabit a universe far stranger and more dynamic than our peaceful existence on Earth suggests, where the forces of annihilation and creation dance together in patterns of breathtaking complexity across the vast theater of space and time. In witnessing their destruction, we observe the universe's most fundamental processes at work, transforming matter and energy in ways that illuminate the deepest mysteries of existence, while revealing new possibilities for understanding the cosmic forces that shape everything from the smallest atoms to the largest galactic structures. The scariest exoplanets, too hot to handle, exist as beacons of extremity, marking the boundaries of what matter can endure, while serving as natural laboratories where the laws of physics are tested under conditions that continue to surprise, terrify, and inspire us with their demonstration of the infinite creativity contained within cosmic destruction.